Many believe that stars are the most important astronomical objects, and for good reason. If you think about it, everything we see is visible to us thanks to starlight in one way or another. In fact, our vision itself developed over millions of years, specifically under natural sunlight, adapting to this primary source of illumination. Even artificial light has connections to stars and the Sunday. For instance, artificial lighting often relies on hydrocarbons of biological origin, which wouldn't exist without sunlight, just like coal, which, if it could speak, might tell us stories about the Sunday's rays hundreds of millions of years ago. Or perhaps your home is powered by solar panels, which directly capture the Sunday's energy. Hydropower also owes its existence to the Sunday, as water flows due to solar heating of the Earth. Only nuclear energy seems disconnected though. As we'll discuss later, it too has surprising links to the stars. When we look at the night sky, everything we see is either a star or something illuminated by starlight. The moon, planets, and comets all reflect the Sunday's rays. Even exoplanets, orbiting distant stars, either reflect their star's light or emit heat as a result of stellar radiation. Without stars, the powerful infrared glow of many exoplanets would not exist. Stars, as bright and motionless points of light in the sky, have been known to humanity since ancient times. But their true nature was understood only in the 19th century, when reliable measurements of stellar distances became possible. While earlier thinkers speculated that stars were distant suns, these ideas remained unconfirmed. For example, Tycho Brahe opposed this notion because he couldn't detect the parallax of stars and thus couldn't calculate their distances. His philosophical beliefs couldn't accommodate the idea of stars being immensely distant sun-like objects. In the 1830s, 3 astronomers in different countries and even hemispheres measured the distances to stars. Thomas Henderson, working in South Africa, correctly identified Alpha Centauri as the closest star and measured its distance at roughly 1 parsec, or 3.25 light-years. Although he conducted his observations in 1832–33, the results were published only in 1839, causing him to lose the race for discovery. The formal victory went to Friedrich Bessel, who measured the distance to the faint star 61 Cygni in 1838, determining it to be about 10 light-years, 3 parsecs. Friedrich Georg Wilhelm Struve, known in Russian circles as Vasily Struve, chose Vega, one of the brightest stars in the northern sky. His measurements, published before and after Bessel's, estimated Vega's distance at 4.8 parsecs, known to be closer to 8 parsecs. But knowing distances is just the beginning. Stars are born, evolve, and die even as we speak. For centuries, this wasn't widely recognized, and stars were perceived as eternal, unchanging objects. It seemed logical to assume that these distant suns had always shone and would continue to shine indefinitely. Immanuel Kant was one of the first in modern times to propose that stars are born and die. He also suggested a model for the formation of stars and planetary systems. At the time, discussions often focused on the solar system, though Emanuel Swedenborg also theorized within a Cartesian framework where gravity played no central role. Today, we know that stars form, evolve, and end their lives. This process involves changes in their energy sources, with nuclear fusion as the primary driver. It all starts with hydrogen fusing into helium, as is currently happening in the Sunday and most other stars. This phase, lasting about 90% of a star's life, is the longest stage of stellar evolution. Many of the earliest stars in our galaxy are still in this phase. If you randomly select a star in the sky, T here is a 90% chance it's fusing hydrogen into helium. When the hydrogen runs out, the star undergoes its first transformation. It expands into a red giant, moving to the cooler, more luminous region of the Hertzsprung-Russell diagram. From there, its fate depends on its mass. Massive stars can compress their cores further, igniting new fusion reactions. Helium becomes carbon, carbon becomes oxygen, and the process continues up to iron. These reactions release energy only up to this point. Elements heavier than iron require energy to form. Such elements, including lead and strontium, are created through processes like slow neutron capture in giant stars. But to go beyond iron, something dramatic must happen: a stellar explosion. Low-mass stars live much longer, burning hydrogen slowly. Since the universe is only 13 billion years old, even the earliest low-mass stars, about half the Sunday's mass or smaller, are still alive today. Identifying these primordial stars, formed shortly after the Big Bang, is a critical task for modern astronomy. In contrast, massive stars live shorter lives due to their high luminosity and rapid hydrogen consumption. Stars with masses similar to the Sunday's live about 10⁻12 billion years. Our Sunday, now midway through its life, will never explode. Instead, it will become a red giant, shedding its outer layers and leaving behind a cooling core white dwarf, the final stage for less massive stars. If a star is about 10 times heavier than the Sunday, it will not turn into a white dwarf. At the end of its life, the core will lose stability. By that time, it will mostly consist of iron and begin to collapse. However, this collapse within the star may be halted. When that happens, an immense amount of energy is released. The star essentially falls in on itself, but instead of immediately becoming a black hole, a supernova explosion occurs. This event is crucial not only because it marks the dramatic end of a star's life, but also because it facilitates the formation of heavy elements. Some elements heavier than iron exist in nature, but they are relatively rare. These heavier elements can form in significant quantities almost exclusively during supernova explosions. Massive element nuclei can also arise from the merging of neutron stars or the rapid ejection of material from red supergiants. However, supernovae primarily result from the collapse of massive stellar cores. There are also explosions of supercritical white dwarfs in binary systems, but we'll save those for another discussion. If the star's mass is 1020 or even up to 30 times that of the Sunday, a neutron star will remain after the supernova explosion. This fascinating object is highly compact, with an average density slightly exceeding that of an atomic nucleus. At its center, the density is even greater. It's no surprise that such an object possesses extraordinary physical properties. The so-called nuclear density is about 2.3 Cheng 2, 10,142.3 Cheng 2, 1014 grams per cubic centimeter. If the star was initially even more massive, it would likely turn into a black hole, meaning the collapse continues. Everything compresses, gravity overcomes all other forces, and a black hole forms. This transformation might happen with or without an accompanying explosion. Now let's examine rotation. Neutron stars are known for their rapid spinning due to their compact size and high density. For them, the critical rotation period is less than 0.001 seconds. This corresponds to a speed of about 0.05 times the speed of light. Even such dense objects eventually reach a limit where they start shedding material. A neutron star may be born with an extremely short rotation period or achieve it later through accretion in a binary system. Observational data show that nearly all neutron stars have rotation periods of less than 1 second at birth. This can be easily explained. A neutron star forms from the collapse of a stellar core whose dimensions shrink by a factor of about 1,000. As everyone knows, when a spinning object contracts, its rotation speed increases. Simple calculations show that the stellar core can accelerate to fractions of a second during collapse. Fast rotation can even temporarily prevent the formation of a black hole. While the mass of the compact object might be significant, black hole formation depends on the density at the center. Rapid spinning reduces this density, delaying the collapse. Over time, as the newborn object slows down, the final collapse might occur. Such metastable objects are called supermassive neutron stars. Theoretical models often involve these stars to explain two-stage collapses with additional energy release in between. The source of this energy is the rotation of the supermassive object. A rapidly spinning neutron star can collapse into a black hole as its rotation slows and central density increases. As the star decelerates, its internal matter may transition into a new phase. The region containing this new phase, made of different particles, will expand and might lead to collapse. Throughout its lifetime, a neutron star can either decelerate or accelerate its rotation, but never beyond its critical speed. Acceleration requires external forces, while deceleration can occur naturally. Typically, a neutron star begins its life slowing down. A neutron star often starts as a radio pulsar. Even if the radio emission mechanism is suppressed, as in compact objects at the centers of supernova remnants, the deceleration of an isolated neutron star follows a predictable pattern. The star acts as a rapidly spinning sphere with a magnetic field, emitting electromagnetic waves and accelerating charged particles. Franco Pacini first highlighted this in 1967, just before radio pulsars were discovered. Though the pulsar phenomenon was not explicitly predicted, the concept of a spinning magnet emitting waves was established. Emitting waves and accelerating particles requires energy, which is drawn from the star's rotation. Consequently, the spinning slows down, increasing the time taken for each rotation. Energy is carried away by waves and particles. The intensity of this emission depends on the rotation frequency and the magnetic field strength. As the rotation slows, less energy is radiated, reducing the pressure exerted by the neutron star's wind on the surrounding environment. Initially, this wind pressure is strong enough that the pulsar remains unaware of any surrounding matter. But over time, as the wind weakens, the presence of external material becomes more evident. This material tends to move closer to the neutron star due to both its inherent pressure, determined by its temperature and density, and its velocity relative to the star. If the material enters the star's gravitational influence, it will begin to accrete. Eventually, the wind of waves and particles will no longer resist the external pressure, allowing material to penetrate the magnetic field region. This not only deactivates the pulsar mechanism usually, it stops functioning even earlier, but also halts the entire process of generating relativistic particle wind. Once its rotation slows to a critical level, the neutron star transitions to the next stage of its evolution. If the first stage of a neutron star's life is called the ejector stage, due to the active ejection of matter and waves into the surrounding environment, the second stage is known as the propeller. This concept was first introduced by Victor Schwartzman in the early 1970s, but it gained global recognition in 1975 following the work of Andrei Ilarionov and Rashid Sunyaev. During the propeller stage, the infall of matter onto the star's surface is halted by its rapidly rotating magnetosphere, which co-rotates with the star since the magnetic field lines are frozen into the crust. The accreting matter consists of plasma, which is ionized and interacts strongly with the magnetic field. Charged particles in plasma have difficulty moving perpendicular to magnetic field lines. On Earth, this interaction results in the beautiful auroras near the magnetic poles, which is why these regions are called polar. Particles are often described as sitting on magnetic field lines like beads on a wire. While their behavior is more complex, the key point is that plasma is frozen into the magnetic field, making it difficult to move across the lines. As a result, the magnetic field can stop the inflow of matter. If the magnetic field's rotational velocity at a given point exceeds the orbital velocity of the plasma, the field lines act like a propeller, scattering the matter. The neutron star's rotational energy is transferred to the matter through the magnetic field, some of which may escape along the field lines. This leads to rapid deceleration of the neutron star's rotation, making the propeller stage relatively short-lived and rare to observe. Additionally, this stage lacks significant energy release, resulting in dim sources, although some candidates have been identified in close binary systems where matter flows from a normal star onto a rapidly spinning neutron star. As the neutron star's rotational period increases, the propeller effect weakens, allowing matter to reach the surface. This marks the beginning of accretion, during which the star's rotation can either accelerate or decelerate depending on the angular momentum brought by the infalling matter. Angular momentum transfer can spin up the star, while its loss can slow it down. The magnetic field's interaction with the accreting matter generally acts as a brake. In stable conditions, equilibrium is often achieved. This balance is particularly evident in X-ray pulsar-secreting neutron stars in close binary systems where the pulsation period corresponds to the star's rotational period. Here, the energy source is not rotation, but the gravitational potential energy of the infalling matter. Observations show that some accreting pulsars exhibit increasing periods, while others decrease, and their periods often oscillate near equilibrium. This balance is crucial, as models of accretion combined with equilibrium periods can provide estimates of a neutron star's magnetic field, a method frequently used by astrophysicists when no other means are available. In summary, a radio pulsar remains active as long as the neutron star rotates rapidly. X-ray pulsars arise in binary systems when the neutron star slows sufficiently. If the magnetic field remains constant, rotation is the main factor determining the observable properties of a neutron star. However, magnetic fields are not always constant. Changes in magnetic field. Magnetic fields are generated by electric currents, including those in neutron stars. Since these stars are not connected to a power source, such as a cosmic outlet, the currents must decay over time, leading to a gradual reduction in the magnetic field. While this principle is straightforward, the details are complex and filled with surprises. The question of where the currents flow to generate the magnetic field remains open. Often, when scientists say something is unknown, it means multiple hypotheses exist. In this case, there are two primary possibilities. The fields and currents are mainly concentrated in the star's crust, or they are predominantly in the core. In reality, both likely contribute, but the proportions are uncertain. Currents in the crust resemble ordinary electric currents, as the crust text for the innermost part where nuclear pasta structures like spaghetti and lasagna exist is largely metallic. These similarities make crust-focused models popular, as they avoid fundamental complexities. The magnetic field in the core, however, is thought to behave in unusual ways. Protons in the core are believed to exist in a superfluid state where superconductivity arises. Superconductors and magnetic fields interact peculiarly. The field is either expelled entirely or broken into quantized magnetic flux tubes that disrupt superconductivity. Neutron star cores are likely Type II superconductors, permeated by vast numbers of magnetic flux tubes. For the magnetic field to decay, these tubes must migrate out of the core into the crust, where they can dissipate, a process tied to the star's rotational slowdown. However, many uncertainties remain, leading to the common assumption that core field evolution has limited observational impact. We will follow this hypothesis as well. Origin of currents. The currents are remnants of the progenitor star's core. During the star's collapse, magnetic field lines embedded in the core are compressed, preserving magnetic flux. As the core shrinks from thousands of kilometers in radius to the size of a neutron star, the field strength increases by tens or even hundreds of thousands of times, explaining the fields of ordinary radio pulsars. For magnetars, an additional dynamo mechanism is required to amplify the field further. If the currents are primarily crustal, their decay is influenced by electrical resistance, determined by two main factors: defects in the crust's microstructure and thermal vibrations phonons in the hot crust of young stars. As the star cools, defect-related resistance dominates. For strong fields, such as those in magnetars, another process becomes important: the Hall cascade. Complex magnetic field structures in the crust transfer energy from large-scale components to smaller ones, accelerating dissipation and increasing energy release. In any case, magnetic fields weaken over time, with stronger fields decaying more noticeably. This decay mimics rotational slowdown, causing radio pulsars to switch off faster. The transition to the propeller stage occurs earlier. Accretion can also start earlier, but there are more direct manifestations of field decay. The magnetic field has energy, in fact, a significant amount. According to the formula E equals mc, in the crust of a neutron star, the field usually corresponds to a density greater than 100 grams per cubic centimeter. In magnetars, we are talking about many tons per cubic centimeter. This is a lot, and this energy can be released. The crust may even start cracking and breaking apart after the energy of the field decreases, as this is analogous to a decrease in pressure in the crust. The field is generated by currents. We know two main types of energy release from currents. A device either heats up gradually or a short circuit occurs. Both options are realized in neutron stars. First, the gradual decay of the magnetic field leads to the heating of the neutron star's crust. If the fields are large, the effect can be significant, and some neutron stars are observed as X-ray sources precisely because of this electrical heating. Second, short circuits lead to bursts. This is the primary characteristic of magnetars that distinguishes them from other neutron stars. Due to the evolution of the field, its structure can change. The magnetic field has many components. It is not just the butterfly-shaped dipole. It is a set of ultrasound waves, very different components that typically decrease rapidly with distance from the surface of the neutron star. Therefore, on a large scale, the dipole field always dominates. It decays more slowly with distance compared to the more curly components. But near the surface, they play an important role, directing the flow of accreted matter or forming the distribution of surface temperature as the neutron stars cool. Different components evolve at different speeds. Moreover, they can exchange energy. This has now been reproduced in computer simulations. Such evolutionary features can explain, for example, magnetars with weak dipole moments. They slow down like ordinary pulsars, but burst like true magnetars, because they still have strong fields and currents. Only their structure is different. It seems that a strong field cannot be hidden unless you take a thicker bag. A thick bag can be created around a neutron star right at the moment of its formation. After a supernova explosion, a significant amount of matter can fall back onto the collapsed core. This process can take several hours. The neutron star and its magnetic field form much faster. So you can imagine the following picture. In one of these compact objects, a huge plasma flow is flowing. The pressure is so high that the magnetosphere is compressed. Now, it is not the magnetic field lines that dictate to the matter that it must flow to the poles. Now, the matter gives the magnetic lines the command to lie down. The field is pressed against the surface and wrapped in a layer of plasma. Sometimes a lot of matter falls. The mass can be several solar masses. But the matter cannot withstand such pressure. The neutron star cannot withstand such pressure and turns into a black hole. But if only a few thousandths or hundredths of the mass of the Sunday fell, the result would be a neutron star, where powerful currents continue to flow in the crust. But on the outside, we do not see a strong field. These sources are observed, for example, as central compact objects in the remnants of supernovae. They are sometimes called antimagnetars. They are called antimagnetars because, on the period temperature delay diagram, They lie on the opposite side of the main group of pulsars compared to magnetars. With periods in the hundredths or tenths of a second, they possess dipole fields, which are responsible for the slowing down of the neutron star's rotation tens or hundreds of times less than that of radio pulsars. But they won't always remain that way. The field will gradually push its way outward. According to calculations, this can take several thousand or tens of thousands of years, depending on the field strength and the amount of matter that fell onto the surface. That is, antimagnetars should eventually disappear, transforming into something else. It is unclear whether they can later turn into radio pulsars or magnetars, and the answer ultimately should be provided by observations. Thermal evolution. Neutron stars are born hot and begin to cool. The first calculations of this process appeared even before the discovery of compact objects themselves, probably simply because it is associated with complex and interesting physical phenomena. During the formation of a compact object, a huge amount of neutrinos is produced. While the collapse is happening, neutrinos can escape from the rapidly collapsing core of the star, but then it will become too crowded and hot there. For the first minute of its existence, the proto-neutron star is opaque to neutrinos. It gradually compresses, starting from a size of a few hundred kilometers and shedding neutrinos from its surface until, after several dozen seconds, it reaches its final radius and becomes transparent to these particles. Now we can consider the neutron star to be fully born. While the compact object is still very young, the main process in its thermal history is cooling. Neutron stars cool in a rather peculiar way, all thanks to neutrinos. Objects around us cool from the outside. We constantly encounter this when eating, for example, taking a baked potato from the coals. But neutron stars cool from the inside. Neutrinos are very efficient at carrying away energy, and they arise at a high rate under high matter density. Therefore, the heat flow is directed inward, not outward. The interior is colder. A cooling wave runs through the star from the outside. This stage lasts for several decades until the temperature inside the neutron star levels out. So, the interior becomes isotropic. But here, two remarks must be made. First, isotropy does not extend to the outermost layers, the crust, and that is what we observe. While detecting neutrinos from the interiors of cooling neutron stars remains well beyond our technical capabilities, we can only register a neutrino burst during a collapse, as was done once when a supernova in the Large Magellanic Cloud was observed in 1987. The surface of a typical neutron star is much colder than the core. For example, if the inside could be nearly 1 billion degrees, the outside will only be around 1 million. This is due to the relatively thin layer in the outer layers that works as a perfect thermal insulator. The second remark concerns the effect of general relativity. Temperature levels out due to heat exchange. But remember the gravitational redshift. A signal traveling from an area with high gravity to an area with lower gravity will be redshifted. In particular, the energy of each individual photon will be lower. Because of this, the internal parts will be hotter, but the heat flow does not arise since the outer layers perceive the internal parts as redder, that is, colder than they actually are. A neutron star can cool in a region with a higher temperature rather than in a region with a lower temperature. This results in the emission of photons from the surface or neutrinos from the interior. Let's continue our discussion about neutrinos. They can be produced in several elementary particle interaction processes. The most important of these is the so-called direct UR process. It is named after Georgi Gamow. Gamow is generally associated with the neutron which enters its world line. While in Brazil, he and his colleague Mario Schoenberg visited the Urca casino. Discussing the energy lost during supernova explosions, Schoenberg remarked to Gamow that in the process of transforming a neutron into a proton and an electron, And then the reverse process of transforming a proton and an electron into a neutron, energy is carried away by neutrinos just as quickly as money disappears in the casino. This process, when it involves individual protons and neutrons, is initiated only at sufficiently high densities. In the presence of nuclei, such as sodium and neon, the process can start in white dwarfs. Even extreme objects like neutron stars may not always allow this. Only in sufficiently massive objects does cooling occur via the direct UR process, and even then, only in the central regions. However, that's enough. If at least a few thousandths of the solar mass at the center of a compact object is engaged in the direct UR process, energy is lost very quickly. By the way, if neutrons and protons in the dense core are transformed into other particles, in most cases there are analogs of the direct UR process. Thus, massive compact objects must cool quite quickly, even if there are no neutrons at the center and other particles have emerged in their place. But what about the less massive ones? Nature has devised a modified UR process for them. It is worth noting the ingenuity of the staff at the Ioffe Institute, who are not only one of the strongest scientific groups in the world studying the physics of neutron star interiors, but also introduced the terms Urka and Murka into scientific usage. Foreign colleagues might not even realize this to denote the direct and modified processes. This process involves extra particles, so it's less efficient. However, it always works. Besides the UR process, neutrinos can be produced through particle interactions without transformations, for instance through particle scattering. T here is also another exotic possibility. The interiors of neutrons don't transform into weak particles. As a result, UR processes don't convert into weak particles, but those inside neutrons do. Thus, the UR process transforms into weak particles, and those within neutrons transform into weak particles. Temperature sizes give an independent estimate of age if we trust the cooling calculations. They are reliable for ages ranging from hundreds to hundreds of thousands of years, provided the star is hot enough, the direct UR process hasn't started, and no additional heating has occurred. Where does the heating in neutron stars come from? Many different ideas have been discussed, but if there is no accretion, then, apparently, only one version seems truly important for solitary neutron stars. It's the decay of the magnetic field. Magnetic fields are generated by electric currents and decrease over time. Some of the current energy goes into heating the crust. If the fields were strong enough and decayed quickly, which happens in magnetars, the heating will be noticeable. Indeed, magnetars have a rather high thermal X-ray luminosity, up to 100 times that of the Sunday. They are significantly hotter than their cousins without such strong magnetic fields. Some of the energy released during the magnetic field decay is carried inward and radiated outward via neutrinos. For neutron stars in binary systems, there is another source of heating. These are pycnonuclear reactions. If a neutron star is left alone, its constituent elements will reach equilibrium, including the crust. But intense accretion disrupts the equilibrium of the crust. The falling material from above presses on the crust. As a result, it begins to sink into deeper and denser layers. The composition of the material that has sunk now doesn't match the density it finds itself in. This will trigger transformation reactions of elements. These can lead to noticeable heat release, and this is observed. Well-known stories from the 19th century describe sources in binary systems where accretion sometimes stops. One can see how the surface temperature of a compact object changes between accretion episodes. Comparing observational data with calculations suggests that pycnonuclear reactions in the crust are necessary to maintain temperature. This brings us back to the question of the properties of neutron star interiors. Neutron stars are the most interesting objects in the universe. This is easy to prove. Take any object, for example, the core of a star. In principle, with unlimited technical capabilities, one can turn any sufficiently massive object, starting from a red dwarf, into a neutron star if it is compressed. In nature, This is how it happens. The core of a star becomes quite fascinating when compressed, and it's very interesting. Now imagine the core of a star. The object itself is compressed by gravity. Energy sources inside are depleted, and the core begins to collapse. It compresses and becomes more fascinating. In physics, as a rule, when parameters reach extreme values, something new and remarkable appears. With significant compression, matter behaves differently than at normal densities. Very strong magnetic fields change the properties of matter in ways unlike regular magnetic fields. Quantity transforms into quality. So, imagine compressing and compressing an object, and it gets more and more interesting. We can observe extremely fascinating physical processes that don't occur under normal conditions. But if we compress it too much, it won't be the same. And that doesn't mean we can't compress it. We can compress it and keep compressing it. But if we compress it, it will not be the same. And that doesn't mean we can't compress it. Damn, charge. But in reality, black holes are almost always uncharged. Or the charge is very small because charges of opposite signs quickly accumulate on a charged object. So when we compress and create a black hole, we lose some of the interesting physics. Everything requires balance. If we stop at the right moment, a star's core with a radius of tens of thousands of kilometers becomes a ball with a radius of 10 to 12 kilometers. This is the size of a large city. It contains ultra-dense matter not found in Earth laboratories, super strong magnetic fields that cannot be created in laboratory setups. You have very strong gravity on the surface, everything with the prefixes super and ultra, and you can observe this exotic physical diversity. That is, you can directly study the ultra-dense matter that exists in a super strong gravitational and magnetic field, and it's super interesting. Inside these super objects, everything is equally fascinating. Besides ultra-dense matter, there could be superfluidity of protons, neutrons, various exotic states, and new elementary particles. These are extremely intriguing objects to study. Neutron stars and super strong magnetic electric fields could be super strong stars. It's not that simple. It was predicted at the beginning. This started in the 1930s. It all began with the work of Lev Landau, written even before the discovery of neutrons. The article suggested the existence of super-dense stellar configurations with nuclear density. However, nothing was said about the possible origin of such stars or where and how to find them. The real breakthrough came in 1934 when Walter Bade and Fritz Zwicky published a short note in which they correctly predicted that neutron stars are born from supernova explosions and can thus be found in the remnants of these explosions. However, despite this intriguing prediction, no one rushed to search for neutron stars. The problem was that finding a 10-kilometer ball somewhere in the distant remnants of a supernova was very difficult. Eventually, they were discovered by chance, only in 1967. Barr didn't live to see this moment, but Zwicky did. No one could have guessed that if compact objects have super strong magnetic fields, predicted a few years before the discovery of pulsars in the works of Vitaly Ginzburg or Anid Ozerny, and they spin rapidly, strictly periodic radio pulses should form as a result. It's not surprising, experts still debate the nature of the mechanism that generates radio emission from pulsars. And it was precisely such radio pulses that were discovered. The history of the discovery of radio pulsars is itself quite dramatic. It is detailed in many books and articles, but mostly in films that show what we can do. Let us remind you that, since the pulsar signal appeared artificial, the period was too precise and short, almost as if it were a radio beacon or some other device. The first thought was that astronomers had intercepted a message from extraterrestrial intelligence. The first source was even named LGM-1, which stands for Little Green Man 1. At that time, extraterrestrials were already being referred to as Little Green Men. The source was later called Unknown, but it was initially referred to as the first source. It was called literary. The source was eventually given a proper name, PSRB 1919-21. However, its early designations clearly indicated the extraordinary nature of the discovery. In the 1960s, extraterrestrial intelligence was a very fashionable topic. This was probably because humans had just entered space, and it seemed that we were about to travel to the stars, as significant resources were being spent on the search for artificial extraterrestrial signals. Observations and discussions were actively conducted. Large international symposia with leading scientists were held. By the way, the modern skepticism of scientists regarding little green men is justified by the fact that scientists spent about 10 to 15 years seriously investigating this issue, but found nothing even remotely promising. Notably, initially, the programs for the study of extraterrestrial intelligence were called SETI Communication with Extraterrestrial Intelligence. However, it was quickly realized that no contact would happen in the near future. Thus, the term SETI Search for Extraterrestrial Intelligence was coined, and it has remained in use to this day. Realizing that radio pulsars were a natural phenomenon, it was necessary to determine which astronomical objects could behave in such a way. Given the short, stable period, there were only two candidates. They were either white dwarf pulsations or the rotation of neutron stars. Of course, white dwarfs also rotate, and neutron stars pulse, but the periods didn't match. To choose one, it was necessary to measure how the period changes over time. It was clear that both the rotational energy and the energy of pulsations should decrease over time. But in one case, for pulsations, the period would also decrease, while in the other, it would increase. If we consider rotation, energy loss should lead to deceleration. That is, the period gradually increases. Pulsations behave differently. Take an elastic ball and drop it vertically onto a smooth, hard surface. It will bounce. Energy will be lost. This vividly illustrates that, in the case of pulsation decay, the period should shorten. Radio astronomers quickly discovered that the periods of radio pulsars were growing. Just a little. For the period to increase by a second, it usually takes several million or even tens of millions of years. But this increase clearly indicated that we were dealing not with white dwarf pulsations, but with the rotation of neutron stars. Indeed, the rotational energy eventually transforms into radio radiation. And not only that, only a tiny fraction of the total energy output is emitted in the radio range. If a neutron star is a radio pulsar, it radiates not only in the radio, but in all other ranges as well. It's just that this is not always visible. The stability of pulsar radiation makes them useful sources in the economy. First, they can be used as a standard for accurate time. Secondly, they can be used for navigation. And here, radio pulsars visible in the X-ray range are especially well suited. X-ray detectors are becoming cheaper, more compact, and more reliable. Many radio pulsars visible in the X-ray range are bright, stable indicators. They must be used so that they are in good condition with your indicators. They are easy to spot and difficult to confuse with anything else. Thanks to the pulsations of radiation with precisely known periods, they essentially carry individual marks. Now, in Russia, Europe, and the US, systems for satellite orientation based on X-ray pulsars are actively being developed. This is particularly important for spacecraft operating autonomously far from Earth. Not by chance, the position of the Earth was indicated in relation to radio pulsars on the famous plaques with brief information about humanity and our planet placed on the Pioneer and Voyager spacecraft so that intelligent beings could find us if necessary. If a satellite is located in the solar system but far from Earth, it is quite difficult to determine its distance from the Sun with high precision. Observing millisecond pulsars in the X-ray range will allow this to be done with an accuracy of several hundred meters without the need for constant communication. Thus, radio pulsars were discovered. The Nobel Prize was awarded for this, but it wasn't given to the right person. this is also a separate, rather typical story. The main author of the discovery, Jocelyn Bell, did not receive the prize, but what matters is that neutron stars were finally discovered, and people began to study them. Astronomers were lucky with radio pulsars. Neutron stars suddenly had their own sort of bells. It turned out that young neutron stars are not just 10-kilometer hotballs, they also emit powerful periodic radio pulses. But there was another surprise. Unfortunately, the authors of this discovery weren't so fortunate. X-ray radiation from cosmic objects cannot be observed from Earth. It is all absorbed by the atmosphere. Instruments need to be launched into space. Astronomers were able to start doing this in the early 1960s, installing detectors not on specialized satellites but on rockets, whose flights lasted only a short time. However, Riccardo Giacconi, Herbert Gursky, and their colleagues discovered several X-ray sources. One of them was an object named SCO-X1. SCO stands for the constellation Scorpius. This is where the source is located. X indicates that it is an X-ray source. In many countries, X-rays are called X-rays, as Wilhelm Röntgen himself referred to them. Finally, the number 1 indicates that this is the first discovered X-ray source in the Scorpius constellation. Now we know that the source SCO-X1 is a tight binary system with a neutron star. The substance of a normal star flows onto a compact object, being captured by its gravity. This process is called accretion. As the substance falls onto the neutron star, a lot of energy is released. Since the gas is heated to a high temperature, we see a bright X-ray source. This understanding of the nature of SCO-X1 emerged a few years after the discovery, even before the discovery of radio pulsars, but there was no decisive proof. The key argument could have been the rotation period of the neutron star. The matter falling onto it is plasma. It moves reluctantly across the magnetic field lines. Thus, the substance is channeled onto the magnetic poles, heating a small area of the surface. These hotspots are called polar caps. If the cap is facing us, we see a strong radiation flow, and when the neutron star is facing us with its cold side, there is less radiation. As a result, the radiation will be pulsating. These sources are called X-ray pulsars. Sometimes confusion arises between accreting X-ray pulsars in binary systems, pulsating thermal sources in supernova remnants, anomalous X-ray pulsars, and radio pulsars, which are also observed in the X-ray range. These are 4 different types of objects, whose luminosity is related to different sources of energy accretion, thermal reserves, magnetic field energy, and rotation, respectively. But all of them are sources of pulsating X-ray radiation, and the pulsation period equals the star's rotation period. If the pulsation period is short, the source is very compact and strong, otherwise the rotation would tear it apart. Moreover, the properties of the radiation indicate that it comes from a very small object. Altogether, this would be proof that accretion is occurring onto a neutron star. But SCO-X1 does not pulse. X-ray pulsars were discovered only after radio pulsars. So, the chance to detect neutron stars by their X-ray radiation was missed. However, for his significant contribution to the development of X-ray astronomy, Riccardo Giacconi received his Nobel Prize, but that was in 2002 when he turned 70. By the early 1970s, a picture had formed. Young neutron stars are visible as radio pulsars due to their rapid rotation and strong magnetic fields. Older compact objects can become visible if they are in a tight binary system, where matter begins to flow from a regular star to the neutron star. In the old zoo of neutron stars, there were 2 types of creatures, radio pulsars and accreting neutron stars. It seemed there would be no other surprises. Fortunately, reality turned out to be rich in wonders. At first, it seemed like a more or less simple picture was emerging. A supernova explosion occurs and a compact object is born. Indeed, within the remnants of supernovae, within the expanding nebula, we find neutron stars. They have strong magnetic fields, thousands of billions of times stronger than Earth's. They have rapid rotation. They can be born with periods of 10 to 20 milliseconds, or even shorter. This is a very, very short period. The rotational speed at the equator approaches the speed of light. Such an unconventional object. Although, in the end, even the most unconventional ones can turn out to be typical if they all look the same. Radio pulsars seem to be similar to each other, and the most important prototype was considered the pulsar in the Crab Nebula. This pulsar was discovered in 1968. It is designated PSR-B 0531-21. The numbers represent coordinates in the sky, and the letter B indicates that the coordinates correspond to the epoch of 1950. It is located in the nebula, where Chinese astronomers observed a supernova explosion in 1054. In Europe, the year 1054 is marked by the Great Shiftham Split between Rome and Byzantium. It's strange that no one noticed the flash and didn't associate it with the end of the world. Currently, the rotation period of the neutron star observed across all spectral ranges is 33 milliseconds. However, at birth, the period was less than 20 milliseconds. The pulsar's magnetic field is approximately 10,000 billion times stronger than Earth's. 1 second is still fast for us, but it is 100 times slower than others. There is a mysterious neutron star in the supernova remnant RCW, -103. It was found that its radiation changes with a period of nearly 7 hours. However, there is still no full certainty that this is indeed the rotational period of the compact object. For example, it could be the orbital period or something else. This resulted in a whole big zoo of young neutron stars with very interesting properties. Now, in addition to radio pulsars, of which more than 2,000 are known, the following classes of young neutron stars are distinguished. Firstly, sources of soft repeating gamma-ray bursts. Secondly, anomalous X-ray pulsars. These two groups of sources are combined into a single class magnetars. There are about 30 of them. Thirdly, radio-quiet neutron stars in the vicinity of the Sunday, known as the Magnificent Seven. Fourthly, central compact objects in the remnants of supernovae. About a dozen of these are known. They are also radio-quiet like the Seven. They emit thermal radiation, but they are younger. They have shorter rotation periods and weaker magnetic fields. Finally, we should mention the so-called rotating radio transients, or RRTs. These are clearly related to radio pulsars, exhibiting very short radio bursts. However, the nature of the bursts is unclear, and the sources are separated into a distinct class. It is completely unclear why they are so different. It would seem that everything should be roughly the same. There should be a single universal process. The core of the star collapsed, and a neutron star formed. The masses are approximately the same, the radii too. But the rotations, magnetic fields, and speeds are different. That's why they are observed as dissimilar sources. Today, it is a very relevant task to explain why newly born neutron stars appear so different and how they evolve. Astronomers have discovered such a paradox. If we take different types of young neutron stars and determine the birth rate in each population, the total birth rate of young compact objects turns out to be higher than the rate of supernovae with core collapse. A strange result. This means that we are doing something wrong. Of course, one might assume that we have made an error in all the rates, and all in one direction by several times. I think this can be done, but it's unlikely. So perhaps we just can't sum up the birth rates of different neutron stars. Maybe it's not entirely correct to think that they all are born so differently and their life paths never cross. For example, if you were to sum up the birth rates of different groups of people on Earth, boys, girls, physicists, chemists, Spartak fans, CSKA fans, you would find that the total rate is higher than the rate of human births. A person could, for example, be born a boy, get a physical education, and support Spartak. Or a girl, a chemist, a CSKA fan, and then change gender, become a physicist, and start supporting Barcelona. This would be a very interesting evolution. Maybe something similar is happening with neutron stars? That is, there are some evolutionary connections between pulsars and magnetars. Magnetars and the Magnificent Seven and central compact objects, and so on. The energy sources of neutron stars. All these types of sources are currently being actively studied. Different young neutron stars can be observed in various ways because they can emit energy in very different ways. In astronomy, this is always very important, because astronomy is the only natural science where we cannot experiment with real objects of study. Physicists, studying particles, accelerate them, collide them, and see what happens. We can't collide neutron stars, we can only observe from afar. That's why it's important to know how and what kind of energy is emitted in these sources. The discovery of neutron stars with large amounts of energy and strong magnetic fields has generated huge interest among astrophysicists. Because these objects can emit energy from their magnetic fields, it is important to recall that a magnetic field is generated by electric currents. Accordingly, if we have strong currents, strong fields arise. This makes it a bit clearer. It's not so easy to imagine how to extract energy from a magnetic field. But everyone understands that if you insert tweezers that extract energy from a magnetic field, you get a huge amount of energy. If you plug the tweezers into a socket, there will be a short circuit and everything might burn out. Energy from the current is released. On neutron stars with strong fields, short circuits may occur. We don't fully understand yet how and where they happen, outside or in the crust of the neutron star. But a colossal amount of energy is released. In just 1/10 of a second, 10 circumflex 46 ergs are released. The luminosity of the Sunday is 4.5 Cheng 2, 10 circumflex 33 ergs per s-second. That is, the Sunday will emit 10 circumflex 46 ergs in 100,000 years. In a short time, 1/10 of a second, it shines brighter than a large galaxy. That is, a system consisting of hundreds of billions of stars. This is a lot. It's incredibly interesting. And naturally, when it's so much and so interesting, it's very difficult to study because very complex physical processes arise. Scientists are now struggling, using different competing theories to describe these phenomena. On the other hand, we can observe neutron stars simply because something falls onto them. T here is accretion. Every gram falling onto a neutron star gives about 10 circumflex 20 ergs of energy. 1 gram of TNT equivalent is 4 Cheng 2, 10 circumflex 10 ergs, which is 2 billion times less. This is a lot. About 10% of Mach 2. If you take a hydrogen bomb, detonate it, calculate how much energy is released, it will be about 10 circumflex 22 ergs, which corresponds to about 250 kilotons of TNT equivalent. Then, if you take just a stone of the same mass as the bomb and throw it onto a neutron star, much more energy will be released. The most efficient thermonuclear reactions release only about 1% of Mach 2. Accretion releases much more. To get 10 circumflex 22 ergs, you need to throw a stone with a mass of just 100 grams onto a neutron star. Radio pulsars shine not through accretion or energy dissipation from currents. Their reservoir is not just a repository, but also a vault. It is the rotation of the neutron star. Over time, the period it takes for the compact object to complete a rotation around its axis increases, and the rotational energy is inversely proportional to the square of this period. If we start with 1 millisecond, the energy corresponds to radiation with the luminosity of the Sunday over 100 billion years. It's no wonder that young, highly magnetized neutron stars, progenitors of rotational energy, are very bright sources, the true golden youth. Moreover, rapid rotation is not their only legacy. They are also born very hot. Their reserves of thermal energy can last for a long time. It is by expending this stored heat that we observe some compact objects in the remnants of supernovae. The variety of processes involving powerful energy release, which is then converted to heat, cannot be inconvenient. And this is not only for us, but for all. The time we use results in diverse observational manifestations. Therefore, scientists try various methods to study neutron stars using a wide range of instruments. These include radio telescopes, where researchers study radio pulsars and other manifestations of neutron stars in the longest wavelength part of the spectrum. There are also X-ray telescopes, because when there is a lot of energy, the temperature is high, and typically hard radiation is emitted. This is easy to understand. If you need to carry $100, you can take one $100 bill, or $101 bills. Put them in your pocket. The small ones are even more convenient. But if you need to carry $100 million, try calculating how much that will be in $1 bills. It will be several bags. You won't be able to carry that. Therefore, you need to take large bills. There are even special $1,000 bills. In nature, everything is arranged in exactly the same way. When a small area of space emits a lot of energy, it carries it away in the form of the thickest X-rays or gamma rays, and this often happens in neutron stars. They are small and compact, and when they shine, energy is carried away by X-rays or gamma radiation. Continuing the analogy, it can be noted that for large-scale thefts, different shadow schemes are used without the participation of cash. And neutron stars, when there is a lot of energy, lose it by emitting neutrinos, which interact very poorly with matter and therefore can silently leave the interiors of compact objects. But neutron stars also shine in the optical range. For example, take the most famous pulsar. So, neutron stars can have four main sources of energy, rotation, current energy, heat, and accretion. The first three are largely related to how the neutron star was born, from a supernova and the properties of the exploding core. In some cases, if some of the material ejected during the explosion falls back onto the newborn compact object, accretion can also become an energy source related to the parameters of the supernova. Although neutron stars are extremely interesting in themselves, they are especially fascinating to study because they are born in the violent process of a supernova explosion. And we know very little about how supernovae explode. We see hundreds of them each year, and this number is only growing with the introduction of new instruments specifically designed to avoid harmful effects. But modeling such an explosion in detail is very difficult. There is a lot of complicated physics mixed in, and most of the authors of different explosion scenarios have used simplifications. For example, some did not account for strong magnetic fields, some did not consider certain thermonuclear reactions, some approximated gravity, some used two-dimensional models. Until recently, supernovae were not even modeled in computers when calculations were conducted in 3 dimensions. Additional momentum had to be manually added to introduce a piston that would push the material apart. Only recently, in 2012, astrophysicists finally made progress and exploded a supernova in a computer. They were able to account for the effects of general relativity of matter. This allowed them to obtain an explosion and material dispersal. But there is still the feeling that while much has been done, much remains, as the dispersal was achieved only in a 2-dimensional model, while the actual supernova explosion happens in 3 dimensions. Moreover, some potentially important physical processes were not accounted for in these calculations. Now, primarily due to the growing power of computers, scientists are actively progressing and facilitating explosions. But this does not necessarily mean that all these explosions will continue in this direction. Observers constantly throw new and new mysteries into the mix, discovering increasingly strange supernovae. But even if an explosion is successfully modeled, it needs to be compared with a variety of observations. Neutron stars, born from the explosion of a star's core, carry its imprint. For example, they can move very quickly. Imagine you have a compact object with a diameter of 20 kilometers and a mass twice that of the Sunday. It can travel at speeds of several thousand kilometers per second, whereas before the explosion, the progenitor star's speed was only about 10 kilometers per second, so it was practically at rest relative to its neighbors. This situation is possible because if a powerful explosion is made slightly asymmetrical, the recoil will cause the resulting compact object to move rapidly. There is enough energy, and this too needs to be reproduced in calculations. Models of neutron star formation, that is, supernova explosion models, must explain both the large velocities and the distribution of compact objects by speed. How many slow ones are born and how many fast ones. Thus, by studying the speeds of neutron stars and black holes, we indirectly gain information about the physics of supernova explosions. Similarly, the mass, rotation, magnetic field strength, and other parameters of a neutron star carry the imprint of a supernova explosion. Partial fallback of material after the explosion onto the compact object can increase the mass and reduce the observed magnetic field. The asymmetry of the explosion can spin up the neutron star and change the direction of its rotational axis. The better we understand the origin of the initial properties of neutron stars, the better we understand the physics of supernovae. I am absolutely convinced that today, the field of astrophysics studying neutron stars is not only growing but will remain a very active field over the coming years, providing many important results not only for astrophysicists, but for physicists in general. That is, it will be useful for fundamental science as a whole. The connection with the complex physics of a supernova explosion is just one example. Many of us, even those who don't know what a supernova explosion is. But we know that a supernova explosion is one example. Many others arise as we consider how the parameters of compact objects change over time. If we want to study very strong currents or very strong magnetic fields, we need to check the predictions of electrodynamics for these cases, and the only object where this can be done is neutron stars. If we want to have a good understanding of gravity, for example, so that satellites in the solar system are not affected by gravity, and that doesn't mean we can't study gravity on Earth. If we want to study gravity on Earth, we need to study gravity on Earth. Again, we need to check the theory of gravity as a whole and look for extreme objects. These will again be the same neutron stars or black holes. The same applies to nuclear physics. We want to understand how protons, neutrons, and other particles interact with each other, how they transform under different conditions. We also want to know how matter behaves at high densities. On Earth, the highest density under natural conditions is the density of an atomic nucleus. We all remember that atoms are ephemeral formations because although the atom itself is not small, its size is about 0.1 nanometer, it is considered large only because the light electrons, which are more than 1,000 times lighter than protons or neutrons, orbit the nucleus at a distance much greater than its size. The radius of the electron orbit is tens of thousands of times smaller. At the same time, almost the entire mass of an atom is concentrated in a tiny nucleus. Making matter compress even more than it already is in atomic nuclei under Earth conditions is extremely difficult because we face strong nuclear forces. At distances greater than approximately 0.8 Fermi, where a Fermi is a length equal to 10 to the power of minus 15 meters, the nuclear force leads to attraction. However, at smaller distances, a very strong repulsion occurs. This is a very powerful interaction, 10 to the 38th power times stronger than gravity at the scale of an atomic nucleus. It's very difficult to combat. The only way to somehow compress a nucleus on Earth is to accelerate two nuclei, for example, in a collider and collide them. But in this case, you get hot matter. The nuclei travel with enormous energy, and at the moment of collision, This energy is released all at once, producing a cloud of quark gluon plasma. This is good for some purposes, but not for studying how cold, dense matter behaves. You don't get it, or you get it for a very short time with various buts. Furthermore, regular nuclei contain roughly equal numbers of protons and neutrons. This is what is called symmetric matter. What we need to understand is what happens when the symmetry is broken, with neutrons being several times more abundant than protons. The only place where we can indirectly study asymmetric cold matter at high density is in the interiors of neutron stars. Estimates show that at the center of a neutron star, the density can be 10 times greater than that of an atomic nucleus, and significant changes may occur there. This is very important and could lead to fascinating transformations. First of all, matter consists of protons and neutrons, and there are roughly equal amounts of each. But when the matter is compressed, the number of neutrons increases. Initially, nuclei are enriched with extra neutrons. Then, neutron droplets form, and eventually, the nuclei disappear, leaving behind a mixture of protons and neutrons. This process is accompanied by the appearance of so-called nuclear pasta, which becomes part of the process. Since the configurations of nuclear matter and neutrons resemble various pasta shapes, such as long spaghetti or flat sheets, like those used for lasagna, in some models, the central parts of neutron stars have roughly 10 times more neutrons than protons. This is why they are called neutron stars. However, various other transformations can also occur. It may be energetically favorable for neutrons and protons to transform into other particles. There are, accordingly, models in which hyperon stars arise. Hyperons are elementary particles containing strange S-quarks. There are stars where, in the central regions, condensates of other particles form, such as pions or kaons, which also contain strange quarks and are exotic in normal conditions. There are even more exotic models, such as quark or strange stars. We remember that protons and neutrons consist of 3 tiny particles, quarks. They have an interesting property. It is impossible to isolate a single quark and study it directly. If we try to pull a quark out of a proton or some other particle, it will take so much energy that it would be enough to create a quark-antiquark pair. The newly created quark will join the particle we tried to split, and the antiquark, along with the quark we obtained, will form a new composite particle, such as a meson. In other words, we didn't pull out a single quark. This phenomenon is called confinement. Quarks are trapped in particles called hadrons. However, in the interior of a compact star, due to the immense gravity, such high densities are created that quarks can become free in this region. This is referred to as deconfinement. This idea was proposed in 1965, even before the discovery of pulsars by Dmitry Ivanenko and Dmitry Kurtgaloids, almost immediately after the hypothesis about the quark structure of matter emerged. With deconfinement, matter will be disconnected from parasites and will consist not of protons, neutrons, hyperons, or other particles, but specifically of free quarks, a kind of quark plasma, in a sense. This is extremely fascinating if, of course, this scenario occurs in nature. For now, quark matter remains a hypothesis. And once again, the only place where this could be reliably studied is in the interiors of neutron stars. These stars are called strange because, at high density, in addition to the usual up and down quarks, a third strange S-quark is added. The S-quark is part of many elementary particles, such as hyperons. In many models of quark stars, the S-quark is important for their stability, but sometimes theorists manage to do without it. Just recently, the presence of strange quarks in dense matter was considered in the modeling of supernova explosions. This helps increase the luminosity of the emitted neutrinos and their energy, which is important for a supernova to actually explode. Additionally, the collapse may be two-stage, where a neutron star forms first and then a quark star. This leads to additional energy release and also aids in the explosion. The rotation of a neutron star affects its composition. If the period is short enough, this happens because rapid rotation changes the density inside any object. Additionally, the object is flattened along the poles and stretched in the equatorial plane. At a period called the critical period, matter begins to flow out from the equator. Theoretical calculations show that just before reaching the critical period in a compact object, oscillations can arise, which will stop the acceleration of the rotation. The star will start to lose angular momentum, i.e., it will slow down. However, due to these oscillations, the neutron star can become a source of gravitational waves. However, it won't be strong enough for detection by LIGO or Virgo detectors if we're talking about known potential candidates. Optimistic estimates show that the next generation of detectors will be able to detect this effect during the birth of rapidly rotating neutron stars in supernovae, which flare up in nearby galaxies. We have already mentioned that rapid rotation is so important for the fate of a neutron star that it can even prevent collapse into a black hole. For this, a speed close to the critical is required, meaning the period should be about 1 millisecond or even less. Under milder conditions, the period of rotation may be on the order of several milliseconds, and rotation can determine phase transitions inside the compact object, such as the mutual transformation of particles and the structure of the star. For example, let's say such an equation of state is realized, where there is a critical density below which the matter consists mainly of neutrons, protons, and muons, and at higher densities, deconfinement occurs, meaning quark matter appears. If we forget about rotation, the density at the center, where the transition is most likely to occur first, because the density there is the highest, depends only on the mass of the star. Rotating close to the limit alters this natural picture. Now, the density depends not only on the rotation period, but also on its value, which will determine the composition of the interior. Slowing down the rotation may lead to a phase transition in the star. For example, a star in a binary system accretes material from its companion. As a result, its mass increases while the magnetic field weakens, forming a millisecond X-ray pulsar. However, despite the mass increase, the phase transition did not occur because the object spun up. After the accretion ends, the neutron star becomes a millisecond radio pulsar. It can now gradually slow down. At some point, the rotation will decrease enough for the density at the core to rise, reach a critical value, and the transformation of the material will begin. Typically, after a phase transition, a more compact configuration forms a neutron star, which gradually stops being neutron-like. It compresses and thus speeds up slightly. At the turn of the 20th and 21st centuries, several research groups attempted to detect traces of phase transitions in the interiors of compact objects by studying their distribution across rotation periods. However, no reliable results were obtained. Other methods are needed to study the interiors of neutron stars. The main problems in studying neutron stars are, first, that they are far from us, and second, that if we talk about the interior, we need to observe the surface or external processes of the neutron star to infer its internal structure. This presents a typical astronomical challenge. Experimentation is impossible. We can only observe. Scientists are trying to tackle this problem. For example, one can observe cooling neutron stars. This is similar to how doctors, without advanced tools to look inside a patient, used to diagnose by measuring body temperature. Neutron stars are born hot, with surface temperatures of several million degrees. Newly born compact objects, with ages of a few years or decades, are not visible to us yet. The youngest known neutron stars are about a few hundred years old, corresponding to surface temperatures around 1 million degrees. We see this hot surface, meaning we can observe such neutron stars. We may even be witnessing something unique as a star cools right before our eyes. Over several years of observation, the temperature of one neutron star, the central compact object in the supernova remnant Cassiopeia A was noticed to drop by several percent. There is some debate about whether we actually see it. And it's not surprising, as catching the effect is difficult. But this provides us with information about what's happening inside because, as we've said, the neutron star cools from the inside, not the surface. Let's recap. Usually, bodies cool from the outside, and typically, a hot object is cooler on the surface than inside. In neutron stars, the situation is a bit more complex. Although, except for the short period of infancy, they are formally still hotter in the center. The energy is not carried away primarily by photons from the surface, but by neutrinos that escape directly from the interior. A neutron star, except for the first minute of its life, is transparent to neutrinos. Therefore, during the first several 100,000 years, sometimes less depending on the mass of the object, the cooling occurs mainly from the inside. The heat flows from the outer layers inward, where energy is emitted as neutrinos. Therefore, by observing the surface temperature, we indirectly obtain information about what is happening in the depth. In various processes involving different particles, the neutrino radiation rate should differ. Hence, quark stars should cool differently from stars made of protons and neutrons. Hyperon stars should behave differently from objects with a large fraction of pion condensate, and so on. This means that for the same mass and age, compact objects of different compositions and structures will have different surface temperatures. By comparing observational data with theoretical models of cooling different types of compact objects, progress may be made in studying the mystery of their interiors. We can use both observations of individual objects with well-known parameters such as accurately knowing the age and distance data from whole populations. For instance, we can take all nearby young solitary neutron stars with ages less than 1,000,000 years and distances less than a few thousand light years from us and examine their temperature distribution. Can we explain it if all stars are quark stars, or at least half of them? Can we describe this population by assuming that all young neutron stars are rarely heavy enough to undergo direct Urco processes? We can rule out certain structural options for compact objects, but a definitive answer is still lacking, as neither observational data nor understanding of physical processes inside neutron stars is sufficient. Radio pulsars slow down their rotation throughout their lives. However, against the backdrop of continuous rotational energy loss, glitches sometimes occur. The pulsar sharply increases its rotation rate and then continues to slow down again. During such an event, the period decreases by a tiny amount, for example by 1/1,000,000th or even 1/1000,000th of a second. But by the early 1970s, the precision of observations was enough to notice this. These events are called glitches. It was immediately clear that glitches tell us something important about the physics of neutron stars. But what? Two main ideas about the origin of glitches quickly emerged. The first one seems more visual. It's a starquake. Imagine a drop of water in weightlessness. If it's not rotating and no external influences are present, the drop will take a perfectly spherical shape due to the action of surface tension forces. If we start rotating the drop, we get an ellipsoid of rotation. It's flattened at the poles and stretched along the equator. Now, let's gradually slow down the rotation of the drop. It will then slowly return to a spherical shape. Let's replace the drop with a neutron star. Its spherical shape is due to gravity. Its rotation slows down in the pulsar phase, but it cannot smoothly change its shape. After all, it has a rigid crust, so mechanical stresses gradually build up in the crust. Eventually, the moment arrives when the crust can no longer resist these stresses. The crust abruptly transitions to a new state, and the star suddenly changes shape. This is when the pulsar should speed up slightly. A very beautiful idea, but over time it became clear that it's not flawless. It explains the period jump well, but it doesn't explain the gradual relaxation of the rotation rate after a glitch very well. Therefore, currently, another hypothesis is more popular. A few years ago, Formula -1 introduced a mandatory kinetic energy recovery system, KERS. All such systems are now based on battery charging, but there were also mechanical ones among the first. The idea is simple. The car slows down, but part of the kinetic energy isn't dissipated. Instead, it's used to spin a massive flywheel. Later, when additional acceleration is needed, the energy from the flywheel can be transferred to the shaft, and the car will speed up sharply. A similar mechanism likely works in neutron stars. In the core of a neutron star, neutrons in the inner parts can be in a superfluid state. This changes everything. Since superfluid liquid rotates in a strange way, if we take a pot of superfluid liquid and start rotating it, initially, the liquid won't rotate at all. Then, once a critical rotation speed is reached, a vortex will appear at the center of the pot. If we spin it faster, the second, third, and more vortices will appear. But the rest of the liquid won't rotate. The properties of these vortices are quantized, and their number corresponds to the rotation rate of the vessel. The faster the rotation, the more vortices. The slowdown of a neutron star's rotation is related to the forces acting on its crust. The crust is rigidly connected to the star's core, but not to the superfluid neutrons in the inner crust. Therefore, while the whole star slows down, the neutron fluid in the crust still rotates, as it can, meaning through vortices, with the same speed as before. The difference in rotation speeds accumulates, but this can't continue indefinitely. Eventually, the vortex system abruptly rearranges and their number changes. Now, the neutron fluid adjusts to the overall rotation speed of the star, meaning it slows down, but the system is closed. The superfluid liquid has transferred the excess rotation to the crust, which we observe. As a result, the rest of the star speeds up a little. A glitch occurs. By observing radio pulsars, we see the rotation speed of the neutron star's magnetosphere, which is firmly rooted in its crust. Therefore, by measuring the period, we are measuring the rotation of the crust, which is linked to the core, meaning practically the entire neutron star, except for the superfluid neutrons. The gradual accumulation of the difference in rotation speeds between the entire star and the superfluid neutrons remains unnoticed by us. However, the restructuring of the vortex system is observed as a glitch in the pulsar period. Interestingly, in magnetars, a phenomenon called an anti-glitch has been observed. As the name suggests, it involves a sharp slowdown in rotation. The nature of this phenomenon is unclear. It is quite possible that the issue here is not with superconductivity, but with strong magnetic fields in the crusts of such objects. The model involving the restructuring of the superfluid vortices is useful because it can explain the behavior of a neutron star after a glitch. However, many questions remain. Nevertheless, glitch data is used to place constraints on the equation of state parameters for neutron stars. In other words, it helps us understand how the matter in compact objects behaves. Many believe that the problem of the internal structure of neutron stars is the most important question related to their physics. As a result, many research groups are exploring different approaches to solving this problem. We have already discussed measuring the surface temperature and observing glitches. Another very clever way to understand what is inside a neutron star is as follows. Imagine that we have a neutron star and we begin to slowly throw matter onto it. Its mass will increase and eventually the star will collapse into a black hole. At what point does this occur? This is in fact a fundamental question. What will we learn by answering it? We will learn the mass at which the star starts to collapse uncontrollably. In other words, we will know how long matter can withstand such abuse before it says, "That's it, I am collapsing into a black hole. You've had enough." We will know the central density at which this collapse occurs. Therefore, it is important to find increasingly heavier neutron stars, meaning increasing the threshold below which matter can still resist collapse. If we manage to find this, we can say that we see neutron stars, for example, with 2.4 solar masses, And then beyond that, we see black holes with 2.5 solar masses. This will practically establish a limit for the transition between these two types of stellar remnants. This will also tell us a lot about how particles interact at high densities when their pressure is no longer sufficient to keep the star from collapsing. In general, the masses of neutron stars and black holes are determined in tight binary systems, which we will discuss in detail later. However, there is another approach that could lead to an exotic way of determining the masses of neutron stars and black holes. This is microlensing. By observing numerous distant faint stars, we can notice that their brightness or position changes because a compact massive objector gravitational lens shares appeared along the line of sight, distorting space with its gravity. Thus, the strength of the effect primarily depends on the mass of the gravitational lens. Accordingly, if the lens is a neutron star or a black hole, we can estimate its mass. Once this method becomes widespread and accurate, a unified mass function for compact objects will be constructed. It is possible that this will reveal boundaries between neutron stars and black holes. Finally, in the coming years, when advanced gravitational wave detection instruments are in operation, by observing the merger of neutron stars, we may learn what is happening inside them. If here on Earth we have to accelerate and collide atomic nuclei ourselves, there we will have a natural experiment of colliding two neutron stars. From the gravitational wave signal of the neutron star merger, we will be able to understand how matter behaves inside them. Firstly, we will observe how neutron stars respond to strong tidal forces. Secondly, we will be able to distinguish the conditions under which a neutron star is formed from the merger, and when black holes form instead. In some cases, we will be able to estimate the mass of the merging objects. Thirdly, the oscillations produced after the merger of a neutron star will allow us to determine its radius with precision. Along with neutron stars, we will learn what happens inside these objects. Along with data on the limiting mass, this will allow us to test the hypothesis of two families of compact stars-neutron stars and quark stars coexisting. In general, there will be a wealth of new data about the interiors of neutron stars. Additionally, mergers of stars containing quark matter should lead to the ejection of a large number of strangelet small clumps of quark matter. Traveling through space, they may even reach us. They could be detected, for example, in cosmic ray experiments, such as the AMS-02 instrument aboard the ISS. But that, apparently, is a matter for the future. So, how is the main question answered today? While we are still waiting for the detection of gravitational wave signals from the merger of neutron stars, the main approach to determining the conditions in the interiors of compact objects is as follows. Theoreticians have many models to describe the internal structure of compact objects. Usually, the equation of state is discussed. It links the density of matter with pressure. Within any such model, the relationship between the mass and radius of the object can be calculated. Now the task is to simultaneously and possibly more precisely determine the masses and radii of neutron stars. Ideally, it is necessary to determine the mass and radius of at least a few neutron stars with high accuracy. Then we can hope that all the theoretical models, except one, will be discarded. In reality, this is a very challenging task. Most often, precise measurements of masses and radii are made in different ways for different sources. Therefore, for some stars, we have accurate mass definitions, and for others, radius measurements. We will discuss this in detail later. The measurements of masses and radii, along with the theoretical curves, are plotted on a mass-radius diagram. This is where the drama of the search for the answer to the main question of neutron star physics takes place. For matter to not start flowing off the equator, the rotational speed there must be less than the first cosmic speed. This means that for each mass and period of rotation, there is a critical radius. If the star is larger, it will start to grow. Quark stars are stable due to strong nuclear interactions. They can be very small, and until they grow too large, their mass is roughly proportional to their volume. That is, as mass increases, the star becomes larger. For ordinary neutron stars, this is not the case. As the mass increases, the matter inside them compresses, therefore the radius decreases. By the way, white dwarfs behave similarly. Depending on the equation of state, objects respond differently to mass growth. Some compress significantly, others change their radius only slightly. The former are said to have a soft equation of state, while the latter have a stiff one. On the mass-radius diagram, such behavior of theoretical curves can easily be seen. In some cases, as the mass increases, the equation suddenly becomes stiff-soft. This means that the density in the star's interior has exceeded some critical value, and a phase transition has occurred. Some particles have transformed into others. For example, the star might have acquired a quark core. These objects are called hybrid stars. Since neutron stars are exotic objects, their main parameters are not so simple. Let's begin with mass. For any ordinary object, such as a star, two definitions of mass can be given. First, we can take the total number of baryons, protons, and neutrons in the object and multiply it by the mass of one particle. For simplicity, let's assume that protons and neutrons have equal masses, and we can neglect the mass of electrons. This is called the baryonic mass. Second, we can look at how the object participates in gravitational interactions and determine its gravitational charge, or gravitational mass. For stars, planets, and other objects of normal density, these two masses are usually very close. For neutron stars, the situation is different. Now, imagine that you take an iron stellar core with a mass of 1.4 solar masses and turn it entirely into a neutron star without ejecting any matter. What is the mass of the neutron star? It is not 1.4 solar masses if we are talking about gravitational mass, but 10 to 15% less. This is the mass that matters in almost all astrophysical manifestations of the object. The fact is that just as the mass of a helium atom is less than the mass of 4 protons due to binding energy, the mass of a collapsing stellar core will be less than the initial mass. The excess energy will be radiated away, mainly through neutrinos, in accordance with E equals mc. In other words, when a neutron star forms, the baryonic mass of the collapsing core has not changed. We assume that no baryon has been lost. But the gravitational mass has decreased sharply over the time necessary for neutrinos to escape from the hot protoneutron star. Now, about the radius. For neutron stars, several values can be determined, and this is related to the effects of general relativity. First, we can measure the distance from the center to the surface. Second, we can measure the circumference around the equator and divide the length by 2π4. Third, we can look at the star from a distance, observe the disk, and determine its radius. All three values will differ. A neutron star is a compact, massive object. Inside it, space-time is governed by the laws of general relativity. Moving outward from the center, we enter regions with progressively weaker gravity. The space-time metric changes. This leads to consequences that must be taken into account when determining lengths, specifically the radius from the center to the surface. It will not be the same as the one measured directly on the surface. Light coming to us from the surface of a neutron star also travels through the space distorted by the star itself. Due to this distortion, we may be able to see part of the far side of the compact object. Therefore, the sizes observed by a distant observer will be larger than those obtained through measurements directly on the surface. Astronomers are making the most of the available data on the masses and radii to draw conclusions about the equation of state. Some progress has been made, but it is still clearly not enough. Special observational programs, including those with orbital observatories, have now been developed to advance in solving the main question of neutron star physics and pinpoint the mass-radius diagram. This will likely be achieved by studying binary systems with neutron stars. At first approximation, a star is a very simple object, and the star has one main parameter, its mass. The masses of the lightest and heaviest stars differ by more than 1,000 times. Other important parameters, such as chemical composition, rotation, etc., vary less dramatically among stars. Therefore, variations in these parameters can be neglected. The mass primarily determines how long the star will live, what it will become, what metamorphoses it will undergo during its lifetime, what its luminosity will be at different stages of evolution, and so on. The lightest stars, which are 10 to 13 times lighter than the Sun, live for an incredibly long time, and reactions in them do not go beyond the transformation of hydrogen into helium. No such single star has yet completed its life cycle in the universe, but someday they will become helium white dwarfs or black carbons. The heaviest stars, 100 times more massive than our Sun, live only a few million years and most often turn into black holes. During evolution, a star can increase its size by hundreds of times, then shed its outer layers and shrink again. This is accompanied by changes in radiation power and temperature. The star's rotational speed, internal structure, and composition also change. However, all these transformations are almost entirely predetermined by the initial mass. If a star is solitary, it can only lose mass during its life. The star blows out a stellar wind, sometimes stronger, sometimes weaker, and the mass decreases. But all these losses are already predetermined by the initial mass. Therefore, it would be great to come up with a way to change the mass, that is, to decrease or increase the mass of the star during its life. There is one good way to do this. Place a second star nearby, and place it so close that at certain stages of the stellar pair's evolution, matter could transfer from one star to the other. For example, when one of the stars expands many times its size, turning into a red giant. This is exactly what happens in binary systems. Thus, a star's life can be longer than in a solitary system. But a star's life in a binary system becomes much more interesting. Its fate can radically change due to interaction with its neighbor. If things are arranged so simply in binary systems, where the main parameter in a star's life can change back and forth, one might ask, what happens in triple systems? In 4-star systems, 5-star systems, and so on? Maybe there the evolution of stars will be even more bizarre? It turns out, no. If we try to create a system of 3 or more stars with approximately equal distances between them so that they could exchange matter, such groupings turn out to be unstable. If you place 3 stars close enough together, their interaction will lead to either one star being ejected, or 2 merging, or a tight pair forming, while the third star spins away. If you place them far apart, stable orbits can exist only if strong interactions between more than 2 bodies are excluded. In nature, this happens naturally during star formation. Unstable systems do not arise or break apart very quickly. That is, one way or another, the only good stable element is the binary star. Interactions involving 3 or more stars simultaneously are impossible. Therefore, discussing triple or higher order systems in terms of mass exchange doesn't make sense. Although there are systems consisting of even 6 stars, they are all pairs revolving around each other at significantly greater distances than the stars in binary pairs. These are, as they say, hierarchical systems. Several bodies in a single dynamic system can weakly interact, slowly changing their orbits. This phenomenon, known as the Kozai-Lidov mechanism, was described by Mikhail Lidov in 1961 for planetary moons. In 1962, Japanese astronomer Yoshihito Kozai reflected orbital changes of asteroids in his calculations. The essence of the mechanism is that the orbit of a light body revolving around a heavy one changes due to the influence of a more distant, relatively larger body. The orbit periodically stretches and tilts. For example, an artificial satellite on an initially highly inclined, albeit circular, orbit can eventually fall onto the planet due to the moon's influence, as its eccentricity increases over time. Such long-term orbital evolution in a multiple star system happens slowly, but in rare cases, it can have far-reaching consequences. The only often occurring situation of intense interaction between more than two stars is called recharging. In dense star clusters, particularly in globular clusters, stars can experience very close encounters. Then, if one star pair meets another pair or a single star passes close by, a change of partners may occur. For a short time, all stars form an unstable system, and then they scatter. For example, paradoxical systems of stars of different ages can arise. In a normal binary system, both stars, of course, have the same age. As a result of the interaction of two pairs, for instance, the companion of one system may swap places with a companion of another, and a single star may take the place in a pair, ejecting one of the stars that was previously in the binary. In general, it's like with people. But this is just a brief episode in the life of star pairs. In higher-order systems, interesting transformations can occur. For example, a system of a radio pulsar with two white dwarfs is known, one of which forms a tight pair with a pulsar, while the other orbits far away. Some systems, consisting of a black hole and a low-mass star, can only be numerically modeled in scenarios where the history begins with a triple system. When discussing hypervelocity stars, we mention a scenario with a triple system. However, nowhere does a simultaneous tight interaction of three stars occur that lasts long enough, longer than a couple of orbital periods. Thus, complex evolution in triple systems and systems of higher multiplicity is possible, but it is broken down into separate stages when only two objects are involved in the interaction. Therefore, detailed study should focus on the evolution of binary stars. Now, binary systems. Star pairs have been studied for a long time. However, it was only in the 20th century that scientists encountered a certain paradox and realized that the exchange of matter between stars must be considered. There is a famous variable star, visible to the naked eye Algol, also known as the demon star. The star got its name due to its variability. Algol is a monster in Arabic and Persian mythology. On European star maps, Algol usually corresponds to the eye of the severed head of Medusa in the constellation Perseus. It is easily visible in our northern sky. It was suspected that this is a binary star system as early as the 18th century. But it wasn't until the late 19th century that this was proven and the properties of each star were determined. Later, it was discovered that there is a third star in the system orbiting the tight pair with a period of almost 2 Earth years, but it was not understood fully by the gods. But we are only interested in the eclipsing pair with an orbital period of less than 3 days. When the parameters of the stars forming this binary system were measured, an amazing fact was discovered. The evolutionary stages of the stars did not match their masses. One star in the pair is heavier, the other is lighter. We know that heavier stars evolve faster, meaning that a heavier star at the same age should always be more evolved. That is, a heavier star at the same age should always be more evolved. Both stars in the pair formed at the same time, of course. In globular clusters where the spatial density of stars is very high, a pair of stars can form as a result of capture. Then their ages will be different, but this does not apply to Algol. Thus, it is logical to assume that the older star in the pair should be massive. But in the case of Algol, everything was the opposite. If the lighter star were more evolved, this would be very strange. And it was necessary to realize that stars can exchange mass, and in large quantities. This strongly affects the observational manifestations. That is, the star that is currently lighter was originally heavier and evolved faster. At a certain stage in its evolution, as is typical for any respectable star, it expanded. However, part of the material didn't just drift away, but instead flowed onto a neighbor. The neighbor increased its mass, while the original star's mass decreased, making it lighter within the system, yet more evolved. This was just the first paradox related to the transfer of material in binary systems. The second one, which is also easy to explain, looks as follows. Not two heavy stars. At the end of their lives, they become white dwarfs. Initially, hydrogen in the core turns into helium, forming a helium core. If the star's mass is insufficient for triggering the next reaction, it sheds its outer layers, resulting in a helium white dwarf. If the mass is enough, carbon and oxygen form in the core, creating a carbon-oxygen white dwarf. If the reaction continues further, an oxygen-neon-magnesium white dwarf forms. All of this seems logical, and we indeed observe helium white dwarfs. However, they are supposed to form from the lightest stars. These stars live longer than the current age of our universe. This creates a paradox. We see white dwarfs made of helium, but they couldn't have formed in the expected time frame. It would take billions of years for them to form. So, where do they come from? They also arise in binary systems. Let the first star have a mass similar to or a few times greater than the Sunday. Such a star evolves over a time span roughly equal to the current age of our galaxy. At the end of its life, this star would have become a carbon-oxygen or even an oxygen-neon-magnesium white dwarf. But, even during the hydrogen-burning phase in the core, the following occurs. The second star, the neighbor, strips away the outer layers of the evolved and expanded star. What remains is a bare helium core. In other words, this artificial stripping is what allows helium white dwarfs to form relatively quickly from massive stars. From solitary stars, they would not have had enough time to form. So indeed, evolution in binaries proceeds very differently. The transfer of material gives rise to very unusual objects such as novae. Let's recall that the word nova here has nothing to do with the star's age. That is, it is not a young, newly formed object. The term originated long ago when the physics behind this phenomenon was completely unknown. Material from a normal star flows onto the surface of a white dwarf, gradually accumulating there. When the density and temperature reach critical values, a thermonuclear explosion occurs. The outer layers of the white dwarf explode, the luminosity increases sharply, and we see a bright object, previously unseen, and call it a new star. Although it is not new at all, some of them flare up multiple times. Without binary systems, such objects would not exist. In addition to novae, there are supernovae. Everyone usually remembers that heavy stars explode at the end of their lives because their core collapses. Matter falls inward, but if a black hole does not form immediately, a rebound occurs. This ultimately leads to a powerful energy release. But this is just one type of supernova. There is another very important class. It is this class that helped cosmologists discover the accelerated expansion of the universe. These supernovae, called Type 1a, are again associated with white dwarfs in binary systems. The thing is, a white dwarf has a maximum mass, known as the Chandrasekhar limit. It is not very large, about 1.4 times the mass of the Sunday, in the case of a realistic chemical composition for such a heavy object. If its mass exceeds this limit, it will lose stability and, as we now know, explode. There is also a theoretical possibility for the collapse of a supercritical white dwarf into a neutron star, but direct observers cannot fully understand what is happening. If it exceeds this limit, its mass will surpass its critical threshold. How can we significantly increase the mass of a white dwarf? Naturally, in a binary system, there are two ways. If the companion star is a normal star, it will fill what is known as the Roche-Lobath region around a star controlled by its gravitational field. Matter will begin to flow onto the compact object, increasing its mass. This can happen either due to the star becoming a red giant or because the components of the binary system are moving closer together. The matter flows much like in nova systems, and slowly the white dwarf's mass may increase. Eventually, it will reach the critical mass, and the dwarf will explode, but this will not be a small burst like in a nova, but a very powerful explosion, and this explosion will be final. There will be no repeat. The explosion of a Type 1a supernova most likely leads to the complete destruction of the object. Recent studies show that this path is not the primary evolutionary channel leading to Type 1a supernovae. First, we do not see enough such systems to explain the large number of Type 1a supernovae, and we should see them, since accretion onto white dwarfs is a very efficient energy source. Such systems would contribute significantly to the background X-ray radiation of different galaxies, which is not observed. Secondly, estimates show that in such systems, the nova phenomenon could often be triggered. During a thermonuclear explosion on the surface of the white dwarf, during the nova flare, a noticeable portion of the accumulated material should be expelled into the surrounding space. This means the dwarf's mass would not increase quickly enough. Therefore, it is now more likely that the second path is the more plausible one. Close binary systems consisting of two white dwarfs often arise, partly because low-mass stars are abundant and no destructive events, such as white dwarf conversions, occur in such systems. Over time, white dwarfs may get closer to each other by emitting gravitational waves. Matter will begin to flow, and the two objects will merge. If they don't go crazy, they will grow. If the combined mass exceeds the Chandrasekhar limit, the merger will create a supercritical white dwarf, and a Type 1a supernova explosion will occur. However, there are also issues here. While a large number of white dwarf binary systems are known, we observe very few systems where the combined mass exceeds the critical limit. Nonetheless, it is currently believed that most Type 1a supernovae arise in this scenario. A Type 1a supernova explosion can be seen from billions of light years away. This allows us to observe such supernovae in very distant galaxies. Since these objects explode in approximately the same way, we can estimate the energy of the explosion. By knowing the luminosity, we can measure the distance to the galaxy hosting the supernova. This allows us to use binary systems for cosmological purposes. So, even if not for the masses, this is still impossible. That's it. Continuing on, when we talk about the economy, at least for cosmological needs and Nobel Prizes, binary systems have been adapted. In fact, the economy is constantly dealing with the products of Type 1a supernova explosions. All cast iron, all steel are linked to them. The explosions of Super Chandrasekhar white dwarfs are the main sources of iron in the universe. This is very interesting. You've probably all seen the beautiful images of the 1987 supernova that flared up in the Large Magellanic Cloud. Beautiful rings, several of them. In projection, they overlap each other. How does such a strange system form? A star, in general, is round. It seemed that it couldn't create very complex objects around it. There should be some spherical symmetry. Very rapid rotation or strong magnetic fields can potentially create cylindrical symmetry of outflows. To produce such an interesting system of rings, once again, a binary system was needed. Once upon a time, there was a stellar pair. One of the stars progressed in its evolution and filled the Roche lobe. The transfer of material began. During the interaction of two stars, a common shell was formed around them, which partially flowed away from the binary system. The gas distribution around the binary, having cylindrical symmetry, became the seed of the outer rings. After the merger of the two stars, a red giant was formed. It turned into a blue giant, shedding its outer shell. The shell then formed the seed of the inner ring. The blue giant's wind compressed this structure, ultimately forming 3 rings. Finally, the explosion of the blue giant caused the 3 rings to glow brightly. In the end, we have a beautiful image. In addition to the remnants of supernovae, interesting structures around binaries also arise in planetary nebulae. A planetary nebula is what remains of the shell of a red giant that it sheds, and it gradually disperses. They are called planetary nebulae simply because centuries ago, when observers looked at such objects through telescopes, they saw a hazy disk that resembled a planet's disk. However, there are also very beautiful planetary nebulae with complex shapes, which look nothing like disks. Specialists suggest that these unusual forms are often also due to binary systems that are inside or were once inside. It is precisely the presence of two stars orbiting a common center of mass that leads to the formation of such a beautiful, unusual structure, which a single star could not usually create. How close can binary systems be? Of course, there is a lower limit and an upper limit. The upper limit of a system's size is connected with the presence of other stars nearby. Their influence, through tidal forces, can affect the binary system and potentially tear it apart. Therefore, very wide binary systems are inherently unstable. A passing star can either capture one of the stars of the binary or simply disrupt the system. This can lead to fascinating processes. Interaction between two binaries can result in star exchange. The dynamics of multiple star interactions are rich and give rise to quite unusual objects. Additionally, the combined influence of galactic objects and the galaxy's gravitational potential affects binary systems and contributes to the upper limit even during their formation. As a result, binary systems with a distance greater than 1,000 billion kilometers rarely form approximately 1/10 of a light year. Now, what about the lower limit of a binary system's size? Naturally, when a binary just formed, the hardest lower limit is simply the sum of the star's radii. They must not merge immediately upon formation, so newly formed stars, even the lightest ones, are unlikely to be only 1,000,000 kilometers apart. However, as a result of evolution, even tighter systems can emerge, since the star's sizes can significantly decrease in later stages. Throughout their evolution, stars can expand, and it's important that one does not end up inside the other. That would mean they merge, and the binary system would not survive, creating a single object. On the other hand, during their evolution, stars can converge significantly. For example, if one of the stars expands and forms a large shell around the binary, the stars within this shell will come very close, which allows for the formation of very interesting systems. The tightest binary system today consists of white dwarfs. They complete an orbit around each other in just 5 minutes, with an orbital speed exceeding 1,000,000 kilometers per h-hour. Naturally, the system must have contracted significantly, because initially such a compact binary system could not have been created. One normal star would have simply overlapped with the other. An interesting result of star convergence is the so-called Thorne-Itkoff objects, which were proposed in 1975 by Kip Thorne and Anna Itkoff. Essentially, they resemble a hypothetical object from Landau's 1938 work, a compact object of nuclear density within a normal star. Thorne and Itkoff not only examined the properties of such objects in detail, but also discussed potential mechanisms for their formation. These unusual creatures arise in close binary systems that have survived the first supernova explosion. When the second star turns into a red giant, the components of the pair begin to converge. As a result, a neutron star may be absorbed by the giant. Surprisingly, these objects are difficult to detect, and there is currently no absolutely confirmed Thorne-Itkoff object. The thick shell of the red giant hides what is happening in its core. Astronomers attempt to detect Thorne-Itkoff objects by looking for anomalies in the chemical composition of the outer layers of the swollen stars. The best candidate so far is the star HV 2112. Anomalies observed in all previously proposed candidates have been explained by processes occurring in the cores of evolved stars, primarily through the S process. An example of an evolutionary sequence in a binary system. A system of 2 stars with masses of 12 and 9 solar masses undergoes a long chain of transformations. At one stage after the supernova explosion, a young radio pulsar appears in the binary system. Then, an X-ray pulsar forms. On the penultimate stage, a Thorn, Itkov object forms. Finally, a Thorn, Itkov object collapses into a black hole. It all begins with 2 stars of 9 and 12 solar masses. The more massive star evolves faster and fills its Roche lobe. Some of its mass flows onto its companion, which then becomes more massive, and some is dispersed around. As a result, the orbit becomes tighter. The initially more massive star explodes, creating a neutron star. At first, it is in the stage of a radio pulsar. Then, the second star evolves, expanding into a red giant, and begins transferring mass onto the neutron star. An X-ray pulsar forms. Some of the mass does not manage to reach the compact object, and a common shell is formed, carrying away angular momentum, the system's orbital angular momentum. At this stage, the system also becomes tighter. As a result, the neutron star enters the giant, forming a Thorn-Itkov object. There are several ways to make stars in a binary system converge. In addition to the formation of a common shell, this can also be related to so-called magnetic stellar winds. A star's wind of particles is captured by its magnetic field, and by using the field as leverage, the stellar wind can efficiently pull the system's orbit apart. This can result in angular momentum transfer, effectively slowing down the binary's rotation. This mechanism works for systems with red dwarfs. At a certain stage, when the binary has already become very tight, the stars converge due to gravitational wave radiation. Gravitational waves carry away angular momentum, making the system more compact. Thanks to them, white dwarfs, neutron stars, and black holes can merge with each other. Another very interesting type of object related to binary systems is the so-called hypervelocity stars. Usually, stars near the Sunday move relative to each other at fairly high speeds, around 10 to 20 kilometers per second. This is comparable to the speed of artificial satellites or planets around the Sunday. In the galaxy's disk, stars are present almost everywhere and always. These stars move relative to their neighbors at this typical speed. In addition to the disk, the galaxy also has other components, such as the galactic halo. While stars in the disk move roughly in the same plane, halo stars can orbit in any direction. The velocity dispersion around the galaxy's center at the Sunday's orbit is about 200 kilometers per second. But these objects are still bound to our galaxy, and no special mechanism is needed for their formation. They move this way from birth. Recently, in the 21st century, so-called hypervelocity stars have been discovered. Their speed reaches 500, 600, 700, or even 800 kilometers per second. These enormous values make the star no longer bound to our galaxy. It is leaving our stellar island forever. It may fly toward another galaxy or even enter it, although the latter is unlikely. It may just remain entirely isolated and drift in intergalactic space, eventually turning into a white dwarf. If we don't consider black holes, how do these stars form? These objects were predicted just before their discovery in the 1980s. The accelerator for these stars is the supermassive black hole at the center of our galaxy. If a binary system, not working for single stars, passes very close to a black hole, the black hole can tear apart the system with its large and increasing tidal forces. One star becomes a satellite of the black hole, and the other acquires a very high velocity. Hypervelocity stars are therefore most commonly observed to come from the center of the galaxy. However, there may be other mechanisms as well. Not all hypervelocity stars, of which several dozen are known, travel directly from the galactic center. But this is undoubtedly the main mechanism, and it also requires that we initially have a binary system. It is difficult for a single star to reach such high speeds from a black hole. An exotic mechanism for accelerating singles was proposed in 2015. A star must approach a supermassive black hole so closely that it begins to be torn apart by the tidal forces. However, if the star is not completely destroyed, the remaining shredded star may acquire a speed of up to 1,000 kilometers per second. In this way, even a single star can be accelerated. However, it is unlikely that more massive black holes are needed in our galaxy. With binaries, it's easier, or with triples. Recently, a surprising hypervelocity star was discovered. Observations showed that it is flying from the galactic center, but it appears too massive. If we estimate how long it should have taken for the star to travel from the galactic center to its current location, we encounter a paradox. Such massive stars do not live long enough. The explanation required the involvement of a triple system. After passing close to a supermassive black hole, the system lost one of its stars. The remaining pair accelerated to the level of hypervelocity stars. But during the flight, the hypervelocity binary merged. The newly formed star not only has a mass equal to the sum of the masses of the original components of the binary system, but also appears more massive due to the recent merger that heated the star. Similar properties are exhibited by so-called blue stragglers, which are mainly found in dense clusters. These objects also appear more massive, brighter, and bluer than expected. Interaction with other stars. However, the fastest star in the galaxy today, US 708, did not accelerate due to interaction with a supermassive black hole. As a study published in 2015 shows, it was part of a close binary system that was disrupted by a supernova explosion, most likely a Type 1 supernova. The star's speed is 1,200 kilometers per second. But could a star be accelerated to even higher speeds, possibly close to the speed of light? Apparently, yes. Again, a binary system is required, but this time it consists of two supermassive black holes. When galaxies merge, such monstrous pairs often emerge. Recent calculations have shown that such a pair of black holes can accelerate various stars to speeds of tens of thousands of kilometers per second. It would be exciting to hitch a ride on a hypervelocity star and travel to another galaxy. If the star already has habitable planets, it would be possible to undertake such an intergalactic journey with their inhabitants. The journey would take hundreds of thousands or even millions of years. However, being on a habitable planet near a normal long-lived star, an intergalactic colony could succeed. Relativistic binaries. Relativistic binaries are systems where at least one of the objects is very compact. Thus, to describe such systems, relativity theory is necessary. Both special, so-called special, and general relativity are required. In English, relativity theory is referred to as the theory of relativity. Therefore, compact objects and systems containing them are called relativistic. These are usually systems with neutron stars or black holes. In the future, we hope to discover binaries containing both a neutron star and a black hole. Binary systems play an important role in the astrophysics of ordinary stars. The main reason astronomers use binary star systems is to measure their masses. Since it is nearly impossible to measure the mass of a single star accurately, we need something to orbit it, and the star must also orbit another body. More precisely, both stars must orbit the center of mass. Fortunately, there are binary systems where we can measure the masses of the stars. Then, when we see a single star, we can say it is similar to one of the stars in a binary system for which we have measured the mass. So, we estimate the mass of the single star and conclude that its mass is of a certain value. This is generally how it works. Though, as usual, reality is a bit richer and more complex. Formation of a binary star. Why did a pair form rather than a single object? A collapsing cloud of gas and dust always rotates. In fact, everything in space rotates. The more it collapses, the faster it rotates. The faster it rotates, the more difficult it is to prevent further collapse. The centrifugal force can halt the collapse, but the collapsing matter struggles to stop rotating, which is needed for further compression. As the cloud collapses, its rotational speed increases so much that forming a single more compact object becomes impossible. To avoid this, the collapsing mass can be split into multiple objects. In this case, if we reduce the rotation, we can separate it into two parts. Each part will rotate around the other, but each can collapse further and eventually form a star. Thus, we convert the excess rotation of the collapsing cloud into orbital rotation of a pair of objects. If splitting into two parts isn't sufficient, one of the fragments may divide further, forming a hierarchical system of two parts, which makes things even more complex. However, if we compress rotation enough, it usually stops after the first or second turn. In this way, a system of two stars can be formed, or even multiple pairs of stars. Now, let's imagine we have a binary system. Let's assume, for clarity, that both stars are massive. Over time, one of them, the more massive one, evolves faster than its neighbor, completes its evolution, explodes, and forms a neutron star. The second star also completes its evolution and creates another neutron star. Thus, we end up with a system of two neutron stars. Before this, at some point in their evolution, the pair could consist of a neutron star and an ordinary star that hasn't yet turned into a relativistic object. These are fascinating systems. In them, we can measure the masses of compact objects, including black holes and neutron stars. Mass measurement of compact objects. Measuring the masses of compact objects is crucial, especially when studying the internal structure of our superobjects. The measurement of compact object masses is key to proving the existence of black holes. The first discussions of these objects, as a possible interpretation for observed sources, began in the late 1960s and early 1970s. During this period, systems consisting of a relativistic object and a normal star were discovered. Material flowing from a normal star onto a compact neighbor releases a lot of energy because the material is accelerated by gravity to a very high speed. If it falls into a black hole, it reaches light speed by definition. For a neutron star, the material falls at a slightly slower speed, but still, when it reaches the surface, it has high kinetic energy. This energy is released, resulting in an incredibly bright source. In the 1960s, X-ray astronomy emerged, and in the early 1970s, new astonishing sources were discovered one after another. It turned out that we often see binary systems where material flows from an ordinary star onto a compact object. In such cases, we can measure the mass of the compact object, and for some of them, this mass is quite large. What does this mean physically? For example, if we have a compact object with a mass of 3, 4, 5, or 10 solar masses, it cannot be made from ordinary matter. We must assume that the system contains a black hole, as neutron stars cannot be so massive. There is an upper limit for neutron stars around 2 to 3 solar masses, although we don't know it exactly. When a relativistic star reaches this limit, it collapses into a black hole. Therefore, compact objects with sufficiently large masses cannot avoid turning into black holes. This does not apply to ordinary stars, which can have masses of 100 or 120 solar masses. They have an internal energy source, and the pressure within the material prevents collapse into a black hole. But in the case of X-ray binaries, we are sure that the second component is not an ordinary star. Many methods of measuring mass and radii are tied to binary systems, especially when simultaneous measurements of these parameters are required. We are able to determine the masses of ordinary stars accurately only in binaries. Observations allow us to determine the orbital period and the amplitude of the radial velocities for each star. After that, the only unknown parameter remains the angle at which we observe the orbital plane. This can be determined, for example, if the system experiences eclipses. Then we can immediately calculate the masses of both stars. This also works for systems with neutron stars. Most of the time, we don't see the compact object itself, but if it is a radio pulsar, the observation of its period change allows us to determine the orbital velocity and projection onto the line of sight. If the neutron star is an X-ray source, we can observe the accretion disk in the optical range, which also gives us the orbital velocity. Sometimes X-ray observations of the disk allow us to set an upper limit on the size of the neutron star. This is because in the X-ray range, we can detect an iron spectral line. When the material from the accretion disk emits it, we can determine how far from the neutron star's center this occurs. This is related to one of the effects of general relativity gravitational redshift. The greater the shift, the closer to the chart it occurs. And if we need to maximize the reduction in speed, Tibetan Moon is a gravitational redshift. The larger it is, the closer it gets to gravitational redshift. The greater it is, the closer it is to the gravitational center, and thus to the surface of the neutron star, where the disk approaches. As a result, the spectral line stops being narrow. It, as astronomers say, grows a red shoulder. The determination of the maximum shift of the line for a given source provides the radius of the inner boundary of the disk. And of course, it cannot be smaller than the radius of the star. Often such estimates are useful and allow us to discard equations of state that predict too large objects. The radius of a neutron star can also be estimated if thermal radiation from the surface is visible. The spectrum of such radiation is quite universal. It depends on the composition of the atmosphere of the compact object, but this is often correctly accounted for. Based on observations, we can quite accurately determine the temperature. If we know the luminosity at 100 degrees, we can determine the temperature. If we know the luminosity at 100 degrees, we can immediately calculate the emitting surface area based on the known temperature. If the radiation is steady, then most likely the entire surface is shining, not some hot spot. In the case of a neutron star with the given luminosity and temperature, we will obtain its radius. This will be the radius that is visible to a distant observer. It is larger than the radius used on the mass radius diagram by the equator. To obtain more accurate information about what happens at this temperature, we must know the gravitational mass of the object. For progress in studying the properties of matter in compact objects, it is best to simultaneously measure both the mass and the radius. Usually, at least two methods need to be applied for this, since due to the effects of general relativity, the observation usually defines a combination of mass and radius. For example, consider the measurement of gravitational redshift. It's like a plane. If we see that there is gravitational mass in this place, we can measure the radiation value of the radius of the inner boundary of the disk, but now the source of radiation is right on the surface. Redshift characterizes the compactness of the object, how small it is for a given mass, or how massive it is for a given radius. Such an observation would allow us to measure the mass-radius ratio, the one that is counted along the equator, which would give a straight line on the mass-radius diagram. Unfortunately, there are no suitable lines in the spectra of neutron star radiation. At one point, it seemed that gravitational redshift had been measured, but alas, it was a false alarm. But even if we were able to measure gravitational redshift, a second method would be necessary so that we could highlight a short segment on the mass-radius diagram line, or better yet, a point. One of the classes of close binary systems with neutron starbursters provides an opportunity to add another method. In these sources, matter flowing from a normal star accumulates on the surface of the neutron star until a thermonuclear explosion occurs. As a result, the shell begins to expand. Then, the matter returns. But this is not a rapid fall, because the matter is supported by a powerful radiation flow. The matter seems to hover over the surface. At this time, the luminosity is critical. It is called the Eddington luminosity, named after Arthur Eddington, who first considered such a situation. Here, it is important that light exerts pressure. Gravity tries to drop the matter onto the surface, while radiation tries to push the matter away. Analyzing the balance between gravity and radiation ultimately allows us to determine the combination of mass and radius, as Eddington and others used this equilibrium. In this case, the matter that supports the surface depends on the mass of the attracting object. Finally, high hopes are pinned on the analysis of pulse profiles of X-ray pulsars. To solve this problem, several space projects are even planned. One of them is called NICER. This system of X-ray telescopes will be installed on the ISS. Another much larger project is still in the planning stages. It is the European satellite LOS. The idea of the approach is that careful modeling of the pulse shape allows us to determine both mass and radius simultaneously. Again, this is due to effects of general relativity. Neutron stars distort space so much around them that we always see their backside, at least partially. Light rays only move in a straight line if they are emitted perpendicular to the surface, that is, exactly along the radius. This leads to the possibility that such stars may have narrow pulses, and pulsations will be strong. For massive stars with small radii, we always see enough of the opposite side for the pulses to spread. Detailed analysis of several dozen objects should allow us to accurately determine the combination of mass and radius and clarify the issue of the equation of state of neutron stars. The prize at stake is the Nobel Prize. Binary systems have provided a unique opportunity to study black holes. Of course, we do not see the black hole itself. We observe the matter flowing into it. Usually, the matter forms a disk around the black hole, and we see radiation coming from the inner parts of the disk, which are only a couple of radii away from the event horizon. It may be even less if we do not see it, but if we see it, we see it. If we see it, we see it. If the black hole is rotating quickly, and this is so far the only good way to learn something about these amazing objects. The main argument in favor of the existence of black holes is precisely related to relativistic binary systems. There are so-called nova stars. In reality, as we have already said, they are old, but they got their name because they can quickly increase their brightness and suddenly appear in the sky. These are binary systems. Matter in them flows from an ordinary star to a white dwarf, accumulates, and an explosion occurs. A similar thing can happen with a neutron star. In this case, we have a binary system, a neutron star plus a normal one, and matter flows from the normal to the neutron one. It gradually accumulates on the surface, and at some point, a thermonuclear explosion occurs, quickly covering the entire surface. We see such objects. They are called X-ray bursters, from burst explosion. And it can be reliably proven that this is indeed a thermonuclear explosion on the surface of a neutron star. At the same time, there are systems that are extremely similar to the systems with bursters, but no explosions occur there. The only way to explain such sources without explosions is to assume that the compact objects involved in these binary systems are bursters. Burster-bursting systems simply do not have a surface. In other words, to put it simply, there is a black hole there. Like the horse of Baron Munchausen, into which it poured and from which it poured, it is impossible to quench it, so it is impossible to wait for a thermonuclear explosion from accretion onto a black hole. If we discard the black hole version and imagine that there is some surface there, bursts should occur, provided that the radius of our alternative object does not differ from the radius of a black hole by more than a few percent. Therefore, the existence of such binary systems, similar to systems with bursters with matter flowing in but no bursts, is one of the most reliable arguments in favor of the existence of black holes. We believe that in the coming years, direct proof of the existence of black holes will be obtained, and it will be thanks to binary systems. If we output in the system that there are binary systems in the system, we cannot say that there are two very massive stars, each of which lived its life and created a black hole, and then such a system, losing orbital angular momentum through the emission of gravitational waves, can evolve into the merger of black holes. This will lead to the appearance of a gravitational wave burst, and current generation detectors will be able to register it. At the same time, the existence of black holes will be proven. The fact is that based on the shape of the signal, we can tell whether the event horizons of black holes interact, or whether objects with solid surfaces merge. True, there is still a subtlety here, because if we imagine a hypothetical alternative to black holes, where the radius of the surface exceeds the radius of the event horizon by an infinitesimal amount, a final answer will still be impossible to give, or at least very difficult. If no flashes are detected, we will not be able to figure out what happens with black holes. If no bursts related to the last moments of Hawking radiation of black holes are detected, gravitational wave data will remain the most direct and reliable evidence for the existence of black holes for a long time. Binary systems can be quite diverse, and one type of X-ray sources associated with binary systems is so unusual that a new type of black hole had to be invented. X-ray sources emit radiation when matter from one star flows to a compact object, and energy is released. It would seem that the more matter flows, the larger the radiation flux, but in reality, there is a certain limit to the luminosity. Everyone remembers that light can exert pressure. This fact was discovered in the late 19th century and is now a well-understood phenomenon. Crucial experiments were conducted in Moscow at the Faculty of Physics of Moscow State University by Professor Pyotr Lebedev. There are many examples of how light pressure affects well-known objects. For example, artificial satellites are slightly deflected by solar radiation. But the Sunday is a rather weak source, especially if we are talking about satellites moving tens and hundreds of millions of kilometers away from it. With stronger radiation, the effect, of course, becomes more noticeable. Now imagine this picture. Before us is the surface of a neutron star, and we throw matter onto it from somewhere above. Each kilogram of falling matter leads to the release of energy greater than in a typical atomic explosion. The more matter falls, the more energy is released. And the more the radiation will push against the falling matter, eventually some equilibrium is reached. We can continue throwing matter, but the luminosity will not increase beyond a certain point. A part of the substance will simply be carried away by the radiation flow. In other words, a certain limiting value will emerge, characterizing the outgoing radiation. This is the Eddington luminosity we've encountered before. Eddington luminosity depends on how strongly light interacts with matter. Photons interact with electrons, while gravity pulls heavier protons and neutrons downward with greater force. Therefore, the limiting values for hydrogen plasma, where each electron has one heavy particle, and for helium plasma, where each electron has two heavy particles, will be different. However, the composition of the matter during accretion does not differ significantly between various sources. Therefore, the primary dependency of the Eddington luminosity is on the mass of the object undergoing accretion. A balance is established between the pressure of light and gravity. The greater the mass, the stronger the gravity. The stronger the gravity, the greater the limiting luminosity. In other words, only very massive objects can have high luminosity in a stable state without an explosion. For neutron stars, the Eddington luminosity is about 100,000 times the solar luminosity. If we have a black hole formed from a regular star, the limit might increase slightly, by a factor of 10 or in rare cases by tens of times. In neutron stars, the total energy output can exceed the Eddington limit due to the complex shape of the emitting region, thanks to the influence of a strong magnetic field. However, even in the most extreme cases, the limit only increases by less than 100 times. Thus, it is still very difficult to imagine how an X-ray source based on a compact stellar mass object could have luminosity in the range of several million or even tens of millions of solar luminosities, yet we observe such sources. There are no such sources in our galaxy. But once good X-ray telescopes capable of distinguishing individual sources in distant galaxies came into use, the first such instrument was the Einstein Observatory, astronomers began to discover objects with abnormally high luminosity. Importantly, we're not talking about sources in the centers of galaxies, which might be associated with supermassive black holes. Astronomers also made an effort to rule out situations where we cannot clearly resolve the details and mistakenly treat a group of several objects as a single source. Of course, the observers also eliminated any matter at the center of galaxies. But this does not mean that we can't resolve everything in detail. These are incredible background sources, such as distant quasars accidentally projected onto a much closer galaxy. The simplest explanation for the anomalously powerful sources, which astrophysicists immediately proposed, is the hypothesis that there is a black hole with a mass not of 5, 7, or 10 solar masses, as expected from standard stellar evolution, but rather hundreds or even thousands of solar masses. This would help answer many questions and explain the properties of these ultra-powerful sources, so called because of their great luminosity. The problem, however, is that it is unclear how such black holes appear in nature. This remains an active subject of discussion. There may indeed be a way to create intermediate mass black holes, intermediate between stellar mass black holes and supermassive black holes. Alternatively, it might be possible to explain these ultra-powerful sources in a more trivial way by assuming that the radiation does not descend symmetrically, but rather is directed like a spotlight. If the spotlight is aimed directly at us, we see a very bright source, think that it has huge luminosity, assuming it radiates equally in all directions, but in reality, it primarily radiates in our direction. Each year, new interesting data on ultra-powerful sources emerge. The current picture is that these objects are a mixture, an assortment. There are compelling arguments suggesting that the most powerful of the known sources, for example, the HLX-1 source in the galaxy ESO 243-49, actually contains very massive black holes with masses ranging from several hundred to 10,000 solar masses. This is an important point for researchers because they cannot determine what this is. It may not be the case. However, if we look at the masses of accretors, we can see that their number in different sources, containing several thousand solar masses, is notable. On the other hand, reliable estimates of the masses of accretors in several ultra-powerful sources suggest typical stellar mass black holes. One source, to everyone's surprise, turned out to be an accreting neutron star. In 2014, this remarkable discovery was made by Matteo Baschetti and his co-authors who conducted observations with the new star X-ray satellite, the source XZ. The X2 source in the well-known nearby galaxy M-82 turned out to be an X-ray pulsar with a period of just over 1 second. Black holes cannot be pulsars, so this is definitely a neutron star. Surely, ultra-powerful sources will continue to surprise astronomers. For example, hypotheses are being voiced that some of them may be linked to magnetars. To form certain interesting types of objects, the star must rotate very quickly. There are perhaps 2 main classes of objects thought to form from very rapidly rotating stellar cores magnetars and long gamma-ray burst sources. Magnetars are neutron stars characterized by very powerful magnetic fields. For such a magnetic field to form, meaning for the currents that support it to exist, some mechanism is required. The thing is, magnetic fields that sustain them can be destroyed or reduced. But if we understand that magnetic fields are not enough to explain the formation of magnetar fields that can arise in existence, this means they need to insert several stars that could be inserted into magnetic fields. But a magnetar only consists of fields that permeate the core of the star. Hank Sprout showed that the fields in the core are insufficient to explain the parameters of magnetars. Therefore, additional generation is required. A generator, dynamo mechanisms. In these processes, the energy of matter's motion, including rotation, is converted into electric field energy and thus into magnetic field energy. Accordingly, something must rotate in the dynamo. For an effective dynamo mechanism to work, the core of the star that will become a neutron star must rotate very quickly. But here is the problem. Massive stars have a very strong stellar wind, and the power of the stellar wind causes the star to slow down its rotation. Furthermore, the expansion of stars, such as during the red giant phase, also slows them down, which can affect the rotation of the core. Thus, we would expect that by the end of their lives, most massive stars rotate very slowly. If the outer layers are well coupled to the inner ones, for example, due to the magnetic field, then such stars and their cores should rotate slowly as well. Therefore, neutron stars will form with relatively slow rotations. Not too slow by neutron star standards, this might be a rotation period of a few hundredths of a second, but we want it to rotate in 1,000th of a second. Only then can we generate a large magnetic field. This means the core of the star needs to be additionally spun up. Where can we spin up a star? Again, only in a binary system. If a star is in a binary system, several possibilities arise for the star to rotate faster. First, the star can spin up if it accretes matter from a companion. Second, in very tight systems, the stars can spin each other up via tidal interaction. Finally, the stars can simply merge. The resulting star will then have a very strong, very rapid rotation. Therefore, it is likely that the primary channel for magnetar formation is evolution in binary systems. Our calculations showed that a significant portion of magnetars may form in binary systems, where at least one of the stars has undergone the spin-up stage. There is now observational evidence supporting this model. In 2009, Ben Davis and his colleagues published an article in which they described the observation of one of the magnetars. In 2014, a paper by Jason Clark and his co-authors presented compelling arguments that the anomalous X-ray pulsar CXOUJ 164,745 formed in a binary system. It is possible that there is a set of evolutionary channels that could account for the formation of such systems. In this case, the formation of a neutron star may be associated with gamma-ray bursts, the most powerful explosions in the universe. Their total energy output surpasses that of some supernovae. In the current standard model of long gamma-ray bursts, this intense energy release requires the rapid rotation of the collapsing star's core. As a result, when a neutron star is born, a black hole is formed after the collapse. If the core is rapidly rotating, a thick, rapidly spinning disk of matter forms around the hole. In such a system, as calculations show, an ultra-relativistic outflow and directed radiation beam can be generated. If this radiation reaches Earth, we register a gamma-ray burst. Note that in this scenario, rapid rotation of the star before the explosion is again essential, and we cannot generate a gamma-ray burst otherwise. We do not know how to achieve this if the star is not, or has not been, part of a binary system. Some gamma-ray bursts are also explained by magnetars. Thus, massive stars mostly form in binaries. In about 10% of cases, the system does not break apart after the supernova explosion. This means that we can observe a radio pulsar paired with another star. However, ordinary pulsars have a short lifespan, lasting only about 1 million or 2 years, after which the radio emission mechanism shuts down. This is primarily due to the slowing of their rotation rate. A reduction in the magnetic field might also contribute. To make the pulsar work again, it would be helpful to spin it up to a very short period. But how? Evolution in a close binary system offers such a possibility. After the formation of a neutron star in a binary system, it cannot be spun up. However, this does not mean that it cannot be spun up. In a close binary system, the second companion continues its life. As we mentioned, each star has a region it controls. This volume is known as Roche lobe. At some point, a regular star may fill its Roche lobe, and matter will begin to flow onto the neutron star. The overflow can happen in 2 cases. Either the star itself expands and becomes a red giant, or the system simply becomes tighter. In a close binary system, when gravitational wave radiation or the magnetic stellar wind causes the components to spiral inward, mass transfer begins. The flow of matter affects the neutron star in three ways. First, it spins it up to millisecond periods. Second, it slightly increases its mass. The third effect is quite unexpected. The magnetic field of the neutron star decreases. We already mentioned that magnetic fields weaken when the currents that generate them decrease. Currents diminish because of increased resistance, which occurs when the crust of the neutron star heats up. So, accretion will heat the crust, leading to a reduction in the magnetic field. Furthermore, the falling mass of matter will cause the old crust, where the currents flow, to sink deeper into the interior. There, the damping of the currents will occur more quickly. The result is an unusual object, a neutron star with a rotation period of several milliseconds and a magnetic field hundreds of times weaker than that of regular pulsars. Such an object can also emit radio waves. This millisecond pulsar has the characteristic of being very slowly slowed down because of its weak field. As a result, they live for billions of years. Therefore, we can detect many such objects. The first millisecond radio pulsar was discovered in 1982. The idea that pulsars with low magnetic fields can appear in binary systems was first detailed over 40 years ago in the 1974 work by Boris Kumberg and Gennady Bezhnevati-Kogan. Gradually, gaps in our theoretical understanding of these systems, as well as observational data, were filled. In due time, X-ray millisecond pulsars were discovered. This occurred in 1998. These sources are precursors to millisecond radio pulsars. The accretion onto the neutron star is still ongoing in the system, but if it stops, radio emission generation will begin. And this has recently been observed. X-ray and radio observations demonstrated that some neutron stars with millisecond rotations cannot appear. However, in binary systems, neutron stars are sometimes observed as X-ray pulsars and sometimes as radio pulsars, depending on how much material is flowing onto them from the second companion. Millisecond radio pulsars can also be isolated objects if the system disintegrates or the second component disappears completely. This can happen either due to complete mass transfer or evaporation. The radio pulsar gradually heats its light partner, which leads to its slow evaporation. Such pulsars are called black widows, after the spiders whose females kill and consume the males after their evaporation. Millisecond radio pulsars are valuable because their masses can be measured very accurately. Astronomers actively use this property. The heaviest objects which spark the imagination of theorists dealing with equations of state are the double millisecond pulsars. Some of them have masses slightly exceeding 2 solar masses. It is not surprising that their partners are most often white dwarfs. In such systems, the second star has had time to evolve to completion, and thus it has transferred much of its mass to the neutron star companion. Therefore, the heaviest known neutron stars were likely not such from birth. There are also radio pulsars in pairs with other neutron stars. Fewer than 10 such binaries are known. Initially, 2 massive stars must have formed in such a system, and it must have survived 2 explosions. For us to detect the pulsar, it must live long enough to become a millisecond pulsar. Systems of 2 compact stars help study the theory of gravity because a pulsar is a very precise clock. The second neutron star creates a powerful gravitational field in which these clocks are forced to operate and send us signals. For the discovery and study of the first such system, which provided indirect evidence of gravitational waves, Russell Hulse and Joseph Taylor were awarded the Nobel Prize in Physics in 1993. At the beginning of this century, an even more astonishing object was discovered. A doubly double radio pulsar, PSR-JO 737-3039. This discovery was made by Martha Burge and her co-authors. In this system, both neutron stars were observed as radio pulsars. The older one appeared as a millisecond pulsar, while the younger one was seen as a regular pulsar. Currently, the young pulsar is not visible because its beam no longer reaches Earth due to precession. However, in the future, we will be able to observe both pulsars in the binary system again. This is a very tight system, so a merger will likely occur soon in astronomical terms. Within a few months, several relativistic objects were observed that would take years or even decades to see in other systems. Moreover, this system allowed for fantastically accurate measurements of the masses of both neutron stars. Additionally, this system is very close, about 600 parsecs from the Sunday. Therefore, such pairs are likely not rare. This conclusion is extremely important for estimating the number of neutron star binary mergers that will be observed using the Virgo and LIGO detectors. The discovery of Martha Burge's close doubly-double pulsar system confirmed the optimistic estimates of the number of mergers made by theorists based on population synthesis calculations. Two very strong scientific groups have worked or are still working in this field of research in Russia, at Inosin and Geish, with Vladimir Lipunov, Konstantin Paznov, and others. The fate of close systems of two neutron stars is predicted by general relativity. Through the emission of gravitational waves, the stars will lose orbital angular momentum and eventually merge. When two massive compact objects fall toward each other at nearly the speed of light, an enormous amount of energy will be released in various forms. Astronomers hope to discover an even rarer object, a pulsar, paired with a black hole. These are rare, occurring about once in several thousand regular radio pulsars. There are currently about 2,000 known radio pulsars. Since no such system has been discovered yet, it is necessary to build a very large instrument capable of detecting thousands of new radio pulsars. The first such instrument will be the Chinese radio telescope with a large dish as its antenna. This instrument will be similar to the famous Arecibo radio telescope. It should at least double the number of known radio pulsars at that time. With a high probability, among the new pulsars there will be at least one pair consisting of a radio pulsar and a black hole. This could potentially lead to another Nobel Prize. If they are unsuccessful, in a few years, the Square Kilometre Array Telescope system will begin operations. One of its tasks will be to detect all the radio pulsars in the galaxy that are emitting in our direction. Thus, binary systems may produce some of the most interesting objects in the universe. The most powerful explosions, the most unusual types of neutron stars, and possibly even extraordinary black holes may be involved. A lot of new discoveries about these marvels are expected to be made through the detection of gravitational waves. To be continued.